All right, let's give everybody a little bit of time to settle in, but welcome everybody, and good morning, good evening, good afternoon, and welcome to this Introduction to Graph Data Science workshop. Super excited to have you all join, and very excited to have Henry Colley present today. Henry Colley is one of our masterminds behind the Graph Academy platform, which is our online training platform where you can find dozens of workshops like this one today for self-paced learning, from introduction to graph databases onto general application development with certain drivers and programming languages, onto obviously graph data science as we see today, or AI focused learnings like build a knowledge graph with LLMs. And I'm happy to have you all join today. It's going to be interactive. It's going to be very hands-on. So I'm hoping you have a good time. I'd like to get a couple of things out before Henry takes over. This workshop is recorded. So if you miss some bits, or you want to come back to something that was maybe a little bit too quick, or maybe something wasn't quite clear the first time around, you will get the video recording afterwards, so you can always rewatch this session today. Obviously, all the materials come alongside with it, so you'll see an email probably end of the week or early next week about this in your inbox. So don't worry about that. If you have any questions, anything you want to clarify, there is a Q&A section to the right of your should be to the right of your screen, next to the window where we are at the moment, and it says Q&A, and you can type any questions you have in there and put them there. We should find some time during the session today to look at questions and answer some questions. If not, we'll try to catch you up after the session is over. So it's always good to have you put in your questions there. There's also a chat window just for saying hi, or if something really is broken, shout there. We can have a look at it as well. But for questions, please use the Q&A section, because otherwise it's going to be a little bit too confusing, and sometimes the chat goes by a little bit quickly, and then you don't see the questions anymore, and it's a shame, because we missed your question then. I think with that's more it out of the way. Henry, floor is yours.
Hello, Harry. I will just start by saying yes, there will be scheduled breaks. Hello, Fernando, and hello, Jan. Hello, Debashish. Thank you all for joining. I am Henry Colley. I'm a curriculum developer at the Graph Academy, and I particularly specialize in the graph data science generally and graph data science plugin. Just so I can kind of get a sense of where everybody is, can you all, don't worry about the Q&A right now. I know Alex is probably going, but I say that out loud. If any of you have used graph data science before, could you chuck that in the chat and just let me know? If any of you haven't, then let me know, and just kind of explain your experience of data science in general, if you can, just so I can kind of get a sense of this. But without further ado, I'm going to intro you to what we're doing today. It is technically 4 hours, but we'll see how fast we can get through it, and work from there. So I am Henry. We've covered that already. Today we are going to cover these first 3 modules in the Graph Data Science workshop. I will show you on the platform in a moment. But basically, we're not going to do this 4th one. I'm going to leave that for you to do on your own, because there's quite a bit of setup there, and I think it's a good way to explore. And then I see there, Harry, not much, read some stuff on GNN. Okay, cool. Ivar, intermediate. Yeah, Anna tested long ago. Tried out using shortest path in community. Finding algorithms for a social network demo. Nice, awesome. That's basically what we're covering today, plus a little bit extra. Data science expert, but no graph data science background. Holger, don't worry about that. That actually is really, really common. We often go into hackathons and workshops and stuff, and a group of newly graduated data scientists, and we say, how many of you have used graph data science? And they're like, graph what? So don't worry, that's absolutely fine. So today we're going to cover the foundations of using the plugin and what graph data science is. Then we're going to frame everything that we learn in module 1 around a use case where we detect fraud within a peer-to-peer financial network. And then we're going to talk about using graph data science through the Neo4j Python client. You can use Neo4j in a bunch of different ways, and you can use GDS in a bunch of different ways. But the usual sort of standard workflow, especially if you're already a data scientist like Holger, would be to use all of that as part of your usual Python workflow. That said, I personally absolutely adore using it just in the browser because it's super simple and you can kind of get that static understanding. So we are going to go to the Graph Academy website. I'm going to give you the link for that in a second. And then we're going to enter the course. Here are all the links that you need. So I'm going to copy this into the chat. Okay, so if you could follow that link in the chat, that is going to take you to the super important, super well-made notes document. We spent hours and hours on this. So, please don't take it for granted. Up here, you have the link to this very notes document. Then down here, you've got the Graph Academy URL. You will need to sign up to Graph Academy, and I highly suggest that you do this. So sometimes with these workshops, people don't sign up and don't enroll and then don't follow along. They just kind of listen to the sound of our dulcet tones. Generally, for this course, I highly suggest that you enroll. The reason for that is if we go to the course, it's pretty intense. So even if we go down, we're covering the GDS workflow, algorithm categories, projections and structure, projection practice. So there's a little bit of hands-on in there for you to actually, use your cognitive faculties upon. And a lot of this stuff is very conceptually difficult to understand, but very practically easy to understand. So once you're actually running the code and once you're actually experiencing the feedback from that code, it becomes a lot easier to understand. If you're not doing that, then you're going to find it pretty difficult, I think. So yeah, definitely follow that link and then go to Graph Academy at neo4j.neo4j.com. And that will take you to Graph Academy, where you just sign up. And then once you've signed up, we will go to the Graph Data Science Workshop, which is here. And that should take you to this page. Once you're on that page, then we will get started. So for now, I'm going to give you all like 5 minutes to kind of set that up. And if you can let me know in the chat, once there's sort of a critical mass of people saying, yes, I've done that, then I will just continue. I do not have access. Can you give access? Yes, absolutely. This should have been for public consumption. There we go. Done. Okay. Here's the link again. And you should all have access now. Yes. Boom. I see we have anonymous dinosaur, anonymous fox, anonymous coyote, anonymous bat, anonymous capybara. Ooh, boom. I wish I knew who that was. Capybara. Such an odd one. Cool. I see 32 total viewers. Anonymous hyena, anonymous gopher, quokka. Huh. Works now. Thanks. I can access. Awesome. Not a data science user. Kevin, not a data science user as such, but very keen to learn more. Have done some basic trainings from Graph Academy. Yes, that's what we like to hear. Kevin, what have you done at Graph Academy? Also not very experienced with GDS, but need it for pharma use cases. Yeah, GDS and pharma go together like butter on toast, or in my case, olive oil on toast, or sometimes olive oil and butter on toast. Just starting a POC with a vendor, trying to educate myself in parallel. I know that feeling, Joella. Yes, I've used it for biomedical graphs. Fatima, boom, yes. I joined the session late. Nirav, don't worry, that happens. I actually, as a high schooler, won the prize for most likely to be late to his own funeral. That is a true story. And I'm not proud of it. So there is the link again for you, Nirav. The workbook does not seem to exist. Page not found error. Fantastic. So, graph data science workshop, workbooks, workshop notebooks. That should work. That's odd. That should work. Just to let you know, could be this. Who had said that? Hanka, do you have a GitHub account? Because for those workbooks to work, you will need a GitHub account, and same for you, Fernando. So the way that the notebooks work, when we get to the course, so in module 3, we're going to be doing the Python notebook, and we will have all the code here. This is all Python code here, but that will actually be run in these workbooks here in GitHub code spaces. So you don't need to worry about setup or anything like that. I've set this up as a container. It's going to set up your env and everything for you. So all you need is a GitHub account so that you can click the code spaces button when we get there. I have a GitHub account and I'm logged in. Okay. So what I'm going to do in that case, let me see. Alrighty, Root, give me 2 seconds. Haha. Okay, so it appears to be that when I pushed that repo, it was immediately set to internal. It is now public and it should work for you. Joella, all links blocked by my organization. I'll have to follow along for now and try it out on my own laptop when I get home. Yeah, that's actually pretty common. So that is absolutely fine. I do definitely suggest, Joella, that you go through this on your own. There's also another cool course that is useful for you. Let me just find it. Blah de blah. In the Graph Academy site, if you go to all courses, get started with graph data science. It's also 3 to 4 hours, so it's going to cover basically the first module of this, which we're kind of jumping over a lot of in-depth concepts. But if you go into get started with graph data science after this workshop, then you'll get a lot more time with some of those more difficult concepts. Bhavik, thank you so much for letting me know that that works. And Mariana, Holger, yeah, awesome. Okay, so while you guys are in the repo, we might as well get this set up now, and then we can restart the code space later. Yeah, so if you go into code and then just click on create code space, because the workbooks take about 10 to 15 minutes to set up for the environment, then when we reach that, we'll be all good to go. For now, can you all let me know when you've signed up to Graph Academy and have followed that link to Graph Data Science Workshop and have reached the Graph Data Science in practice, and what you should be on is this page. I will need to use my personal laptop. Thank you, Slim. Actually, all of you, because I know some people are sort of more vocal than others, it would be really handy if anybody who needs to use their home computer could just put that in the chat so we can keep track of that, just to kind of know how many of you that's true for, because we might be able to do something about that in the future. I get course coming soon after signing in. Rishikesh, I will get to that in 2 seconds. Okay, so we have some issues with the workshop not being public again. So I have just messaged someone to set it to public. So we should be able to get that coming soon. Can you get the link for the G Drive doc? Of course you can. There you go. Rishikesh, yes, we are not, in terms of the what to do in the workbook, we're not using that just yet. That's going to come later. But what we will be doing is running these little cells here to explain how you can use GDS via the GDS Python client. But right now, you don't need to worry about that. That comes up in module 3. And to those of you who cannot see the course because it's internal, I do have somebody in the background working on fixing that. Lungile, yeah, so the link is actually 3 comments up. I will check it in here again. Just follow that link, and that takes you to this notes document, and then you can sign up to Graph Academy using the graphacademy.neo4j.com link here, and then you can find the Graph Data Science Workshop link here, which we are currently working on making public. Awesome. So the person in charge of making that public is working on it. They reckon it'll be live in about 5 minutes. So what I'm going to do right now is I'm going to start off with the first few slides, because you actually don't have to do anything for that. And then we'll take a brief 2-minute pause to get you all signed in. And then you can follow along and run the exercises yourself. No worries, Lungile. If you need anything else, do let me know. Okie doke. So in this module, we're going to run through the foundations of graph data science. We're going to talk about what graph data science is and when you're going to use it. Then we're going to go through what I like to call the project, run, write workflow. So sometimes you can get kind of confused with what you need to run and when, and projections particularly, people can find them a little bit confusing. So we're going to really demystify all of that and take you through that. You're going to learn how to create graph projections, and you're going to learn how to model graph projections. And you're going to learn all of this in the context of running algorithms to get insights out of them. So graph data science it can be a couple of things, but when we talk about it, you've got graph data science, the discipline, which is the act of doing graph data science. And lest the Neo4j gods strike me down, I must tell you that graph data science does not have to be done in Neo4j. It is its own thing. It's been around since the 1700s. But we have a plugin called Graph Data Science that you can use to easily run algorithms, project, and so on, and analyze graphs. Other applications include, Network X, which is kind of a classic one. You can use it in Python. It's just a package. And it has a ton of graph algorithms as well. But GDS kind of makes that whole workflow repeatable. And of course, you can save your graphs, which is just immeasurably useful. So in this course, we're going to use Graph Data Science, all caps, when we're referring to the Neo4j product. And when you see Graph Data Science in lowercase, then we are referring to Graph Data Science, the discipline. And if anybody gets confused throughout and needs to clarify that, then please do just pop it in the chat and I will let you know. And then Nirab, you're saying, just to get up to speed with this workshop, could you please let me know what it is I need access to get started? Yes. So in 5 minutes, you will need to access this link. And this is going to take you to this document. And in here, you need to sign up to Neo4j Graph Academy. And then you need to come back to this document and you need to enter the GDS workshop via this link. And then that will take you to this workshop. Currently, unfortunately, it is not live, which is a mistake on our part, but it will be live in about 2.5 minutes. Let's say 2 minutes and 17 seconds. And when that happens, I will let you know. And then we'll take a moment. You can all get signed in and we'll move forward. For now, though, you don't need to do anything. So I'm just going to go through all the slides and get you sort of up to speed so we can really get into the meat and potatoes. So by the end of this lesson, you're going to learn how to distinguish between Graph Data Science, the discipline, and GDS, the Neo4j plugin. You're going to be able to explain how Graph Data Science differs from traditional data science approaches, and they are quite different. Identify the key access points for using the GDS library, and understand how and when to use Aura Graph Analytics versus Graph Data Science, because they are actually slightly different things, even though on the surface they basically do the same thing. So Graph Data Science applies graph algorithms to graph data to analyze patterns in connected data. These algorithms can help you to clean your data sets and uncover insights within them. Now, those are a lot of words to explain really what this picture describes. On the left here, you have a graph. I assume most of you know or understand what a graph is. It is nodes and relationships, and that can take many, many forms. So here's an example graph. And when you run this algorithm, which is called Louvain, which is a community detection algorithm, on this graph, it will identify communities of nodes, and it will label them as being part of those communities. Now, don't worry too much about the specifics of this. This is just to give you a general overview and a general understanding. We are going to go through this in more detail later, and you will be running this. Holger, thank you. The course is now online. You told me before my internal person did. You should work here. So awesome, Jan, yes. So now we are going to take that quick little respite from me talking about this, and you're going to get 2 minutes of me talking about signing into this. So for those of you who didn't hear, you need to go to this document, which is linked currently 4 messages up in the chat panel, not in the QA panel. And you need to sign into graphacademy.neo4j.com. And then Graph Data Science Workshop you need to go to Graph Academy, Neo4j.com, courses, workshop, GDS, and that's going to take you into this. So I'm going to give you another couple of minutes to do that. If you can all just sort of hit me with a critical mass of messages letting me know when you're in, and then I will kind of decide when we can move on. And yes, Jan, thank you for the thank you, and thank you, Holger. Bavik, awesome. Thank you for letting me know. Bavik is in the course. How many of you are in the course? Fatima, yes, awesome. Fernando, woo! Myresh, Anna, Daryl, meat and potatoes, yes. It's all about meat and potatoes. Okay, Stefan, Lungile, we are getting Rishikesh, nice one. Rishikesh, sorry, my apologies. Kevin, Mark, Tony, all right, boom. I would call this a critical mass. So just so that we're all on the same page, both metaphorically and literally, I'm going to go back to GDS Foundations, which will be the first page that you have seen. And if you can just follow my click ballet, we're going to click on Ready, Let's Go. And you should all be on this page. And then down here, you've got 4 options. So we're really going to worry about the first 2 for now. The first one is if you want to operate in slide view so you can follow along with the slides, please feel free to do so. You do not have to. You can just scroll down and read it all this way. And then later on, we don't need it for this particular lesson, but if you click this, this is going to connect you to a Neo4j sandbox. And you can run queries in this. Just like you would in a browser window. And that's going to return like an ordinary database, because here's the cool thing about Graph Academy. It is an ordinary database, and it lives within your Neo4j sandbox at sandbox.neo4j.com. So if at any point you need to get into your sandbox, you can actually find the link here. If you sign into this link here, it's going to take you to the database that is running in Graph Academy. And if you want to download this database, you can actually do that from Sandbox as well, so you can practice with it later. So without further ado, let us begin the workshop in earnest. And I am going to rush through some of these bits and pieces just so we can kind of catch up with ourselves, because I don't want you guys to miss out on anything. But if I am going too fast, either because I'm trying to catch up or because I'm Irish and I speak ludicrously fast, then please do let me know, and I will pause, slow down, and try to answer any questions that you have. Yeah, we were describing how community detection might work on a graph. In this case, these nodes have been identified as part of the same community. So again, we're going to go through that in a little bit more detail later. But you can kind of see just intuitively, and this is why I've put this image here, is you can see intuitively what the algorithm is trying to do. Now, whether or not it's successful or unsuccessful is about configuration settings and the modeling of your graph, which we'll get into. But you can see that it's kind of going, oh yeah, these nodes here, like this node is definitely not part of the same community as this node because it's more connected to this part of the graph. And this node is probably, connected to this, so that's one community. And these nodes, well, they're all kind of in this pentagram shape, so they're all part of one community, and so on. So that's what it's kind of trying to do. And what that allows you to do is to identify groups of nodes, or let's take social media, for example, groups of people represented as nodes who might be more connected to each other than they are to any other people in other groups. And now you can sort of bucket them, and you can say, right, this group of people use this particular platform in a particular way. And this other group of people is significantly different in their behavior to this other group of people. And that's the kind of thing that you can do with graph that you can't really do particularly well in other formats. You can do it, but nowhere near as fast and nowhere near as well. So in traditional data science, for example, you might have tables in relational databases. And I'm sure most of you are familiar with this. I think most people are familiar with the table format and relational table format. So you might see all these attributes. So you'd have your user ID, and they have metadata that is their card number. And that's great. That's one table. And then that might be connected to another table, which is location, which would also have user ID and their location. And then that can kind of quickly spin out of control, because you can have 100 different tables that are all for different aspects of that one entity. And there's a different row representing all these different aspects. And yeah, of course, you can have multiple columns per row, but ultimately you're going to have to separate those tables at some point, because tables are so abstract from reality. They're an abstraction, sort of in the way that time is an abstraction of actual time. And so graph data science finds patterns in connections between entities and their attributes. So the really important thing to remember here is people get confused by graph data because they think it's more complicated than relational data. But what I really want to hit home today is that it's actually less complicated than relational data. It's a lot more literal. So, for example, in this visualization, we are running a pattern or an algorithm called Dijkstra's shortest path. So its only job is to pick this node and find the shortest path in the graph between them. So the reason it's able to do that, imagine trying to do this in a relational database. You just couldn't, or it would take forever. This runs in a split second in Neo4j. You have these nodes that have all of their attributes and their metadata attached to them, either as properties, so like a little table that's on the node, or as another node. So you can have this particular person follows this other person, but this particular person also likes this other thing, and then this other person also likes this other thing, and so you can connect people in a very, very literal way. So when you start thinking about it that way, you realize that graph data is actually a lot simpler in theory and in terms of visualization and practicality than relational data. But we will get into this all very shortly. So for example, traditional fraud detection might flag individual suspicious accounts. So somebody commits fraud or does something suspicious and they get labeled as a fraud risk. And then you have to find some way of using that to predict the behaviors of others who may or CC in English had Dijkstra. That is amazing. Dijkstra. We should make that an algorithm. I'm gonna make that a thing. Thank you, ROC. So yeah, in traditional fraud detection, you've got your user ID, and you might have fraudulent true set to 1, and then later on you might have fraudulent true set to 0 or whatever. So you now have to find some way of predicting the behaviors of the people in your relational data. Now you can do that with machine learning, absolutely. And in some ways, a lot of machine learning tasks are graphs under the hoods. They're kind of like black box graphs in a way. So, but that's kind of a big process. You need to collate all the data. You need to format all the data. You need to make sure it's all in the right order, all your ducks in a row. Whereas with graph data science, you do not need to do any of that because your data is already modeled literally. So we have a user who's sent to another user who is a fraud risk, who's sent to another user who is also a fraud risk, who's sent to another user who is also a fraud risk, who shares an IP address with another user who is also a fraud risk, who shares a card with a user who is not a fraud risk, but who is connected by 2 hops to our original fraud risk. All of this is in the data, very easy to traverse. Our relationships are given equal weight as our nodes. So for example, if you want to traverse 1,000 relationships, it's really, really no bother at all. We will get into that later when we get to the fraud detection module. So the Neo4j graph data science library contains an absolute ton of graph algorithms. I think there's something like 80 plus. We're obviously not going to cover them all today. But what they do allow you to do is once you've got your graph that you want to analyze, you can just sub the different names of the algorithms into the syntax and just run different algorithms on the same graph. There's no other like crazy setup or having to import loads of stuff. It's just there, ready for you to use. And it's endlessly repeatable. So you can access the Graph Data Science library through the desktop plugin, through the Aura plugin, and through the GDS Python driver, which we will be covering later. So Neo4j Desktop, if you don't know, is this beautiful piece of free software. You can download it directly from the website. I use this every single day. I also use Aura every day. But I will say that I use them every day, even before I worked at Neo4j. They're just incredibly joyful to use. So Aura Graph Analytics is a different thing. Aura Graph Analytics, so where GDS will run on the same compute as your instance. So you'll have a graph in your graph that you then project, and it'll be in the same computer. You then run your graph algorithms on that and write back to the main graph. Aura Graph Analytics works a little bit differently. It's on demand, so you can have your data in relational data. You can have it in a graph. You can basically have it in any source that you want, and you can then project a graph into an Aura Graph Analytics session, run all of your graph algorithms on it, and then write back to your original data source. And you are only charged for the time in which you are using Aura Graph Analytics, which is just incredible, because some of these algorithms take seconds to run. So you could spin up a session, run all your algorithms within 10 minutes, and then just put all your data back into your original data source, and then close down your session, and Bob's your uncle, you are done. So you literally have your main graph, create your session, and then you would project any amount of graphs that will fit in that session into that session and run algorithms on them. It runs in Aura as a dedicated service optimized for analytics workloads with no memory or compute resources shared with your data store. So that already. While functionally similar to GDS, Aura Graph Analytics is a different product. And I specify this mainly because there's sometimes a little bit of confusion around it. In practice, it does all the same stuff. There are a few functionalities that it doesn't have, and that's not necessarily because they're lacking or it's a limitation. In most cases, it's just that because of the format that it's in, you don't actually need those anymore. So in some cases, there are some things that maybe you might want, and we're working on those. But for most use cases, Aura Graph Analytics is probably the best way to go. However, today, in order to teach graph data science, we will be using the plugin in the sandbox instance that has been provided for you. And later in the course, we're not actually going to cover this today because I would like to keep all of your attention for as long as humanly possible. And the Aura Graph Analytics module is right at the end. But I do encourage you, once we have finished the workshop today, to please go there and run that session on your own time. Okay, so once you've gotten to the end of this lesson, we just hit progress, and that will take us to the first proper lesson, which is the GDS workflow. So let me know when you've all gotten there and followed along. Just chuck it in the chat, and I will see if I can answer some questions. All your ducks in a row. If that is not Irish, I do not know what is. Oh dear. Oh, R.OC. I could hit you with nothing but Irishisms. All your ducks in a row. Story horse is one that gets people. So where I'm from, which is Wexford, people, they kind of talk like that, and they have a story horse, which is literally the short version of what is the story horse. I'm not sure where it comes from, but there you go. One of my favorites. Please use it, popularize it in your daily life. So I'm going to assume that all of you are with me. I'm going to check the Q&A. Could somebody provide? Yeah, that's fine. Okay, cool. We're all in the chat. Nice. So the GDS workflow. As I said earlier, it is project, run, write. That is our main workflow. And you can repeat that endlessly and endlessly. We're going to talk about in a moment what a projection is, so don't worry too much about that. I promise I will grab myself and shake myself and explain these things as we go through. Mladen Kukak, done my PhD in Carlo. Boom. Yeah, Carlo's nice. Carlo is a really nice town. Awesome. What was your PhD in? So project, run, write. So you have your main graph here, and what you don't necessarily want to do is take your entire graph, which could have loads of different nodes and labels and relationships and different relationship types, and then just run an algorithm on that graph. What you really want to do is you want to project a model of the graph that represents the question you're trying to answer, and then run the algorithm on that. So in this case, we have projected we're going to talk about this more later, so don't worry too much if this isn't clicking yet. We're covering it so that it will click later at some point, and you'll have that like aha moment. So this will be projected into memory, and what we're doing here is we're connecting all of these relationships through intermediates. So where we've removed these purple nodes, we're now replacing those relationships between the purple nodes to the other nodes with one relationship to represent it. Oh, nice. Sorry, responding to Mladen there. Sorry for disturbing the flow, Mayresh. Are we recording this session? Can we access it later? There's a network glitch here, so I'm not able to have a smooth experience. Oh, that sucks. Yes, we are currently recording it. I would imagine that you will be able to get this back later. Alex or Sam or Bron, maybe you could confirm that before I start lying. But I'm pretty sure you should be able to get the recording. So yeah. Then you would, on that graph that you have just projected, you would then run your algorithm. And the example that we've used here is an algorithm called PageRank, which tells you what the most important or influential nodes in a network are. So in this case, they're represented by being bigger or smaller. And then once we have that data in our projected graph, we can run it back to our main graph. Now, that might seem like a lot, but it's going to make sense in a second why we do it that way. So we've basically just covered that. That's what you're going to learn. The reason why we do it this way is, first of all, speed. Running graph algorithms are not simple things. They're running quite a lot of complex computations. Some of them are more complex than others. Some of them have insane computations that they have to do. So it is just faster to run them in memory than on disk. However, if you store graphs permanently in memory, then they're just going to disappear, or you'll have to reload them every time that you want to use them. And that's not ideal either. So Neo4j stores in disk the graph and then projects to memory what the graph that you actually want to analyze, which gives you total flexibility. Also, safety. Sometimes you'll be running these graph algorithms and you'll make changes that you didn't mean to make, or you just want to experiment and, work through some ideas. I do this all the time. I spend like an entire day running a bunch of algorithms just to kind of like see what happens. And if you were doing that on your main source of truth graph, you'd destroy it. So what this allows you to do is run all these graph algorithms in a safe sandbox, basically, on memory. And then only when you're happy with that graph in memory and what it's saying, you can write the results back to your main graph and then persist them forever. And then flexibility, you can run multiple algorithms on the same projection, et cetera, et cetera, et cetera. And then Kevin, should I be able to run this GDS demo in Neo4j desktop as well? I just imported the dump into a new local DB and have the GDS plugins installed. So Kevin, yes, but the dump that you downloaded from GitHub, which is where I assume you got it, is not what we're using in this module. So yes, in theory, you can do that. If you've downloaded the dump from your sandbox instance, then yes, that is identical and you should be able to follow along. There are 3 or 4 different dumps that we're using for this entire course. So just make sure that you're using the right one. If you do want the one that you're using for this module, by the way, I would suggest that you just kind of follow along here, because if you click this, your dump is in here. And you can just run any query that you want in here. And we will be doing that very shortly. But if you do want to download it for later, then you just head into your sandbox. You can find that link here, down here. And in your sandbox, it's not appearing for me, but it will for you. And you can just download that there with those options. Anyway, on with the show. So the graph projected by GDS is an in-memory structure containing nodes and relationships, just like your main graph. And you can there's a few ways that you can create a graph in memory to run algorithms on it. So cipher projection, which is the fastest, it's the most flexible, it's my favorite. It's also the kind of the closest literally to a graph. And then native projection. So we made native projection to help people who are Python native in order to so they wouldn't have to learn Cypher. So you can kind of run the Python native workflow in your Python notebooks, but you can also run it in the browser. You can run it in Aura, and that all kind of works. However, we're not going to cover native right now. We're going to start off with Cypher projection, and then we're going to move into native projection later. The reason for that, in fact, I think I have a little note on that here. Cypher projection is more flexible. It's more readily available across Neo4j products. It's primarily used in the Neo4j browser, but you can also use it via the Python driver. The native projection is also ostensibly simpler, and it mimics the syntax of Python environments. It's primarily used in Python, but people do use it in the browser. In this workshop, we're going to focus on Cypher projection first, and then we're going to go into native. And the reason for that is that Cypher is closer to graphs. So that you can see here, we're going to run this in a second. In fact, you can probably run this now, and it will project for you. I'm just going to get rid of this for a second, though. You can see here that in Cypher, it is representing the actual graph structure that you're trying to project. So source node, actually shaped like a node, has relationship acted in to target movie node. So cool. What is it I want to project? I want to project the actor nodes. I want to project the acted in relationships, and I want to project the target movie. So that's way simpler than to me anyway, the native projection version, which is I want to project a graph, and I want to project the actor and movie nodes in this array and the acted in relationships. So you can run both of these, by the way, and I encourage you to. That probably won't run for me because it already exists. But if you just click the run button, then it's going to run for you. And I'm actually going to gs.graph.drop actors graph. Cool. I'm going to drop that again so I can do this magical thing of running because it's so much fun. When you run your Cypher projection, you're going to see an output of how many the graph name, how many nodes you have, how many relationships you have. And it's the same with native projection. So if we move on and we click run on native, again, you're going to get the same. You're going to get your nodes and your relationships. In the early stages of this workshop, as I said, we're going to work on Cypher, and then later on I'm going to show you how to translate into native projection, because once you understand Cypher projection, translating into native is just really simple, but the reverse is not necessarily true. So once you have your projection in memory, and remember, so now this projection that we have, actor graph native 2 and actor graph Cypher v2, they are living in your memory, and they are not your main graph. Anything that you do to those two graphs will not affect your main graph unless you literally write from those graphs to your main graph. Debashish Mighty, you're saying that you cannot hear me. Am I on mute? Is anyone else having that problem? Because that would be potentially problematic. Hello? Neo4j webinars, we can hear you. Okay, Debashis, I am sorry. I think possibly that might be on your end. We will have the recording afterwards, so sorry about that. Let me know if you get it fixed though. And so then running algorithms is really simple. All we do is we call GDS, and then we add in the name of the algorithm. This is an algorithm called degree centrality. And then we say how we want to run that algorithm. Now, again, there are a lot of moving parts here. So don't worry if you don't understand all of this yet. We are going to cover each of these little dots in sections. So at the moment, this is just an overview. Degree centrality is an algorithm that essentially just counts the outgoing relationships on all the nodes all at once and assigns that as a property to the nodes. So if we run degree centrality on our Cypher graph here, which does not exist, haha, this is what you get for late night updates, because I've called it V2. So if you change that to V2, it will now run here. So I'm actually going to post that in the chat for you. So when you run this algorithm, it's going to tell you, I am unable to connect to the sandbox instance. Nirav. Okay, so I'm going to deal with both of these questions in turn. So Nirav, if you are unable to connect to the sandbox instance, that could be a couple of things. It could be blocked, number one, by your organization if you're on a work computer. That does happen sometimes. Or you might just need to go to inspect and go to application and Graph Academy. If you just click this and then refresh the page, sometimes that does it by clearing it. Doesn't always work. Sometimes it does, but that should cover it for you. If not, maybe go into your sandbox and then just terminate the instance that's running, and then see if that works. Yes, Kevin, thank you so much. Kevin is absolutely right. Tony, I was about to get to you there. You actually already have that graph in memory. So if you want to project it again, then you need to drop it. Amazing, Mladen. That worked. So Mladen just refreshed Chrome and it worked after failure first time. Check ports if they're free. Yes, so Tony, you cannot have graphs with the same name in memory. You will need to drop them to then reproject them. In this case, you see I've got this one same one that you ran, actors graph cipher. If I run that again, you get failed to invoke function gds.graph.project caused by, ignore all this, and then this is the important bit, graph, actors graph cipher already exists. So don't worry about dropping it for now. You can if you want, and then you can rerun it. But for now, just leave it in your memory because that means that you already have it and there's nothing else for you to do. So we're going to mush on now. Cool, that's already in memory. And we were on degree.stream. Okay, cool. So all you're doing here is you are running the algorithm here in streaming mode. Streaming mode means that you are just streaming results to a data frame. So it's not going to persist. It's not writing anything to your main graph. It's also not writing anything to your in-memory graph. And then there are other modes that allow you to do that. But it's a very good way of exporting data to another service or just kind of testing your algorithm results to see if they look right and sanity checking them. And then the algorithm is run on the projection. So in this case, we've named actors graph cipher, which is what we projected earlier. And then a map of configuration options, which in this case, we are not using. And then each algorithm yields a unique set of results, which can be processed with cipher. So you'll get like a big old, table of results, which you can then return separately. In this case, I've returned name and score. So how are we doing in the chat? I got this error, bolt error connection. Yeah, Marguerite, if you go to inspect, go to application, this will fix that error. Go to Graph Academy and then click this up here. So if you click that, that's going to clear all of this and then it should connect for you. Let me know if that works for you. So moving on, there are 5 execution modes for algorithm commands. You've got stats, which allows you to get summary statistics without viewing individual results. And you can see down here, we've got an example, GDS degree, which is the algorithm that we just ran, and stats. And all you're doing is changing this mode and running stats. And then this tells you everything that you need to know about the configuration of that algorithm. Don't worry about what these results mean right now. We're just overviewing what the mode actually does. And then you've got stream, which allows you to view results without storing. And as we just did there a moment ago, you literally just change that to stream. And now it runs the algorithm in stream mode, and it will return those results. And then mutate, which will actually change the in-memory graph, but it will not change your main graph. So it means that you can save results to your in-memory graph, and then you can write new results, or you can add those results to another algorithm and chain results together. And then write is just to write everything from the algorithm straight into your graph, and estimate allows you to estimate the memory required. So for that, you just write estimate actors graph native, does not require, yeah, okay, we will deal with that later. However, let's move on because we will be dealing with this all in very much detail later on. So for estimate, let's just open that up a little bit. What we do is call gds degree.stats.estimate, then we name the graph. So that's the graph that we have in memory, and then we can yield. And then it will tell us that we need 72 bytes in order to run this algorithm. It is an estimate. It could be wrong, but it's usually not wrong. So that can tell you if you need a bigger heap in order to run any particular algorithm. So we'll move forward now. And ultimately, you're going to end most of your GDS sessions by writing your results back to the graph. So call GDS algorithm.write, which is this here. And write is your execution mode. Degree is the algorithm we want to run. And that all lives within GDS, which we call. And then that is going to write results back to your actual graph. So if we run this, you can see that our minimum score is 0. Our mean score of degree, so how many relationships each of the nodes actually has, is 3.4. And the node properties written is 60,193. So that means that degree wrote the property degree with the number of relationships that each node has on each of those nodes. And it did all of this, bear this in mind, in 867 milliseconds, which is nothing. And Nirav, I see that you need help with the inspect steps. Do you still need that, or are you sorted? Okay, I'll keep going. Nirav, let me know if you need me to do that again. And if you do, then I'll pause and do that again for you. So moving on. As I said, you can also write results to your graph projection first using mutate mode. And thank you, Mladen. Yes, I will do them again. So what you're going to do is right-click on the course, go down to Inspect, then go to Application in this top bar here. And in here, you'll see Storage, Local Storage. You want to click on graphacademy.neo4j, and then click this, and then refresh the page. And that should do it for you. And again, we can have another pause later to do that again. So, Fernando, when we use degree.write, we are writing the projection in memory, or we persist it in the memory? No, persist it in the disk. Yes, Fernando. So degree.write is persisting on the disk, and degree.mutate, which is what we're doing here, is persist in memory. And remember, anything that persists in memory only persists as long as that projection exists. So as soon as you drop that projection, everything you did to it disappears, including the graph itself. So if you did not write it back to disk, which you can also do after having written it to the in-memory projection, then that will disappear. We will get to that in a little while. Good question, though. So to persist in memory and not disk, you go actor gds.degree.mutate, and that will mutate to the in-memory projection. And you can see that the output looks identical because it essentially is identical. And it's just writing that to your in-memory projection. So here is a little image that I made to represent this. From your projection, you can gds.pagerank.write to your main graph. You can gds.pagerank.mutate to your projection, which will actually mutate the projection. So these are the same graph in memory, and you have projected and modified this graph. If you have modified this graph, and don't worry too much about this function right now, you will rarely use it in this workshop, and you can find it, but just to explain that it is there. If you have mutated your in-memory graph and you go, oh no, I need to put this on my main graph, all is not lost. You can gds.graph.nodeProperties.write to your main graph, and you will find that in the docs. So that will do essentially exactly what gds.pagerank.write did. That's really useful for if, and we'll get to this in a little while, if you're chaining algorithms and you want to do an algorithm mutate, then use the results of that algorithm to remutate and remutate and remutate. And then you don't want to just write that one set of results to the graph. You actually want to write everything back to the graph. Then you can use nodeProperties.write to write everything back to the graph. But we won't cover that right now in too much detail. We'll just run it quickly for you so you can see. On our actors graph cipher, we have written degree with gds.graph.write, and we just run. And that has written properties to the graph. And that's literally it. That is now persisted to our main graph. So a couple of housekeeping things that you need to know to list graphs, so you know how many you have in memory. It's very simple. It is just gds.graph.list. So we can run that. And we have projected a ton of graphs in this session into memory. They are all sitting in our heap, taking up lots of lovely space. And we don't want them hanging around when we don't need them anymore. So we can drop a graph with gds.graph.drop. So we run that. And that has dropped the graph that we named, which was actors graph cipher. However, we will get to that in a second. You can drop all of the graphs at once. I'm going to show you that in a moment. But what happens when you drop the graph is that the entire projection disappears. And all the data that you had in this projection is lost if you didn't write it back. So you have to write it back. Do not drop a graph until you are certain that you do not need it anymore. But on the flip side, don't keep a graph just in case, because you can always reproject and rerun algorithms rather than taking up loads of memory. If you want to drop all the graphs in memory all at once, I do this a lot. This actually isn't, as far as I know, an official Neo4j pattern. I've not seen anyone else doing this. But I am giving it to you because I use it every single day. Mainly because I'll go, oh yeah, I need this graph. Oh, I need to do this graph. Oh, I'm going to run this algorithm on this graph and then see what that does. And then I end up with 10 graphs in memory and I need to get rid of them all. So call gds.graph.list. Yield graph name will give you all the graphs that you have in memory. And then call gds.graph.drop. And then you specify graph name, which will pull in the graph names that were yielded here. And then from here, yield graph name as dropped graphs, and then return dropped graphs. And when you run that, that will delete all the graphs that you have in memory. Again, we're not going to spend too much time on that, but you do have access to this course at the end of the workshop. So please do feel free to come back to it. For now, we're going to move on to algorithm categories. So as I said earlier, there are 80 plus algorithms in Neo4j. They fall into sort of a few broad categories. We're not going to cover every single category today. We're just going to cover the 5 main ones. So by the end of this lesson, you're going to understand what the 5 categories of GDS algorithms are, what they're used for, because all of the algorithms that we have are very much geared towards using them in practice for an actual business purpose or application. And we're going to match analytical questions to the appropriate category, and so on. So let's jump ahead. And I see that the chat we're talking about, so Nirav, the connection may be blocked by your firewall or proxy server Neo4j. Okay. Nirav, are you on a work computer by any chance? Because sometimes this doesn't happen. This doesn't work because of how we've set up the sandbox, and corporate firewalls will block it. So it would be good to know if that's possibly the issue. Judith, the names you specify in the yields clause are specific to the algorithm you use? No. So that pattern, if you go back to, I'm not going to jump back to it now, but if you go back to it, that is a generic pattern. You can just chuck that into any session and it will grab all of the graph names. So graph name is just what it's called in the output data frame. So when you list a graph, you'll have a column that is graph name, and it has the graph names that you have. And so yield is just yielding all of those. It's just generating a list, basically, of all of those graph names. And then when you call drop and you specify graph name, it's going to take all of those graph names into it, and then it's going to drop them all one after another. So no, you can literally just copy that, chuck it into any instance, and it will just drop all the graphs that you have in memory, regardless of what they're called. So the 5 categories. We have centrality, which tells you which nodes are most important. And examples of algorithms in the centrality category are PageRank, which I'm sure a lot of you have heard of before. It's the Google algorithm. Degree, which is what we just ran in the previous lesson. And betweenness, which tells you which nodes in a graph are the most connective. Again, don't worry about remembering all of this. We are going to cover this in greater detail. In case it hasn't been clear, the general structure of this workshop is we're going to cover everything in like a broad, holistic overview, and then we're going to gradually break down into the details. So we will be covering things again and again. Nirav, you are using a work laptop. Okay, so in that case, that probably means that your firewall is blocking connection to Neo4j. So for now, just follow along here. And then when you get home, you can use this on your personal laptop, and then you should be able to connect. So that is good to know, though. It's good to know how many people that happens to, because it doesn't happen often, but maybe it happens enough that we'll figure out some other way of doing it. So the next category is community detection. So that is what groups exist. No worries, Nirav. Thank you for understanding. So community detection, what groups exist. So that is the first one that we looked at, which was the community detection with all the different sections on the graph. And of course, what groups exist depends on how you define the group. And that's why we have multiple different algorithms for community detection, like Louvain and Leiden, and weakly connected components, WCC, which we will cover later on. Similarity. So which nodes are most like other nodes? So node similarity and k nearest neighbors. Don't worry too much about understanding what that means, because that actually is kind of a weird googly bloobly idea that becomes a lot simpler to understand when you actually start doing it in practice, which we will be very shortly. Then you also have pathfinding, which helps you find the best route. Now, that might seem like it would have one type of algorithm, but actually there are multiple ways that you can find the best route. And depending on what kind of routes and what way you want to find the route, you will change the algorithm you use. So Dijkstra and Jens k-shortest paths. We're actually not going to be running these in this workshop. However, at the very end, should you accept the challenge to go through the Aura graph analytics section yourself, you will get to use Jens K and Dijkstra's. So then we also have node embeddings, which is my personal favorite because it's just so cool. So node embeddings are, hands up, pop in the chat who does already know what embeddings are in terms of semantic embeddings. And if you don't know what that means, and that sounds like a programming language you've never heard of, then please pop that in the chat as well and let me know. But we will be covering that later when we get into Python. So node embeddings take the idea of semantic embeddings and applies that to a graph. They come in multiple forms, depending on what it is you are trying to do. Yes, Kevin, vectors. And you basically turn your node into a vector representation. Now, that's not the semantic properties on the node. That is actually the node itself in relation to all the other nodes. So it is a physical representation. But that can also be enhanced by property features. You can also use semantic embeddings and put them into your node embedding so that you get signal from that as well. There's so much you can do to it. Now, we are not going to go too in depth on that because that could be a 10-hour workshop on its own, but we will briefly cover them later on just to kind of get you started, and then you can go and explore on your own. It's a really, really exciting way to use graph. And Fatima, I do and have used them, would love to hopefully have some more complex embeddings like rotation and translation based embeddings included with Neo4j. Yes. So moving on, start with your question. Who matters most? Is centrality? What groups exist? You use community detection. What's similar to this? Similarity. How do I get from A to B? Pathfinding. How do I use this in machine learning? You would use embeddings. So a note on the mindset. A lot of people come to Neo4j thinking that it is magic. I don't know where they get that idea. It is magic. Sometimes you're using Neo4j and you do get the like, whoa, how did that happen moment. However, bear in mind that these algorithms are not sentient. They do not find frauds. They do not discover communities. You use the algorithm to do those things. Now, that might sound like pedantry for me to say that, and I'm sure some of you are like, oh, yeah, well, obviously. But you'd be surprised how often that misconception persists. They compute the scores and assignments based on the graph structure that you have created, hence why we're going to spend so much time on projections. You have to decide what those results mean. Running degree centrality on one graph means on one type of graph might mean a completely different thing. The results, it's doing the same thing, but the results might mean a completely different thing to running it on another graph. So whether a cluster represents a fraud ring, a department, or noise depends on your own domain knowledge. An example of that we'll get to is you might have a bunch of users connected to IP addresses, right? And you might have 500 users connected to one IP address. And in one context of a graph, in one graph context, you might say, oh, fraud. But also, they could all just be people who frequent the same coffee shop or the same airport. So, yeah, there's nuance to it, and you need to use them with sort of more of a playbook mindset than I run algorithm, it do thing mindset. Fernando, I tried embeddings for semantics 2 weeks ago, but I had to move back to Elasticsearch to ES for now. Hoping this work gives me some insights into how to use it better in Neo4j. Yeah, so you can do semantic embeddings through Neo4j and store them on your nodes. Super useful. It's also really useful if you then create a similarity graph. So you can kind of do graph rag with that, which is awesome. Node embeddings are slightly different to semantic embeddings. They're like another thing that uses the same idea, but is actually encoding a different type of structure. And there's a lot to it. But yes, we will be covering that. And just explore. Just explore. You will learn these things and pick them up just by having fun and failing. And you know, it's not the end of the world if we don't all know everything all the time. So some algorithms have specific requirements. In traditional graph theory, all graphs are undirected. Neo4j is a property graph. We have directionality in our graphs because that is important for a lot of graph operations. So some graphs allow you to have directed relationships, which is where this node points to this node and this node does not point to this node. And then other graphs have, so Leiden, which is another community detection algorithm, it cannot run on a directed graph. It has to run on an undirected graph. And this, again, comes back to how you're going to construct and project your graph. And then some algorithms can take weights. So you can have these relationships, but you can actually weight them. So you can give this relationship a weight 5. You can give this relationship a weight 3. And in the case of Dijkstra's, for example, if you're trying to find a way from this node all the way to this node, then it's going to try and find the cheapest path to that node. So it's not going to follow this path, because this is weight 5, and that would mean that this is actually, even though it might be a shorter path, technically it's a longer path because it's got a higher cost. But again, you can cover that later in module 4. So let's jump ahead and we will move to graph projections and structure. So the way that you project your graph determines what algorithms can see and what they can analyze. So in this session, you're going to learn how to create the projections, understand graph structures, and why this matters for your algorithm results. So by the end of this lesson, you're going to understand how to create cipher projections. You're going to understand the difference between graph structure and node labels, because they're not the same thing. You're going to identify monopartite, bipartite, multipartite, heterogeneous graphs, or heterogeneous, depending on where you're from. Choose appropriate projection strategies based on your target algorithm. So again, the most basic cipher projection command looks like this. You will match what it is you are trying to project. You will create the graph projection using the matched nodes. You will name your projection. You will use the source nodes. You will use the target nodes, and then you will assign the variable g to represent the graph, and then you will return what properties you want from that. So just so we're all on the same page, the graph that we are using in this course, this is actually what I'm calling a Franken graph, because it is actually 2 graphs. And what you have in here and what we're talking about right now is this graph. So we have movies which have been rated by users, movies which have been acted in by people, and some of these people are actors, and some of these people are directors, and then movies are in genres. And then this is another graph, but don't worry about that for right now. So just get rid of that. We have projected the actors who acted in target movie relationships. You are not limited to using the relationships that are available in the main graph. For example, you can use intermediate nodes in your match statement to create new relationships that exist only in the projection. So that's kind of a confusing concept, so I'm going to spend a little bit of time on this. When you match source, actor, acted in, movie, you're getting that first part of the relationship. But let's say you don't want your in-memory graph to be actors acted in movie. Let's say you want to have just one graph of only actors and their connections through movies. How would you do that? Well, what you do is you designate your source as actor, and then you write out that full literal relationship to movie, and then you have acted in backwards to actor, okay? So what this is doing when you create your source target definition down here, that is taking your source, your target, and it is creating one relationship between them in memory. That's a made-up relationship that just kind of passes through the movie nodes. So now you just have actors connected to actors and actors connected to actors. This is super useful for a lot of use cases. So if you could run this, just copy that and run that, and you'll get actors graph, and you'll see that it has fewer nodes, but it has a ton of relationships. Now, the reason for that is that your actors are connected to other actors by a forward-facing relationship, which means that you're going to get directional relationships in both ways because they're both connected to each other equally. And someone is messaging me there. Yes, I am going to deal with that very shortly. So then running that previous projection is going to create the graph connecting actors directly to actors who worked on the same movies. And what you might expect that to do is create this actor acted in movie relationship in that first projection that you ran, the source actor acted in target movie. And let's just make sure that we run that. Cool, already exists. But it's not actually creating this relationship, right? What it's actually doing is it's creating this bipartite graph of labelless node called node is connected to, via a relationship all, so all types, to another labelless generic node called node. So the structure of that graph is still bipartite. It's still in two parts, which we'll cover in a second what that really means. Even though it's got no labels, because the labels are not what defines the structure of your graph. The structure of your graph is how the nodes connect. So those are your partite structures. And the labels are essentially what GDS knows about the properties of those nodes. So what are their labels? Is this an actor? Is this a movie? Your projection has kept the bipartite structure because structure is structure, but it has lost the labels. So a monopartite graph has nodes that cannot be separated into distinct non-overlapping sets. So that means that you could not pull them apart and have one set of nodes on this side and one set of nodes on this side where they only connect to each other. That would be bipartite. They're all just one big mesh of nodes, right? And that's a social network, for example, will probably usually be a monopartite graph. A bipartite graph is a graph where you can separate them into distinct non-overlapping sets. So in our movie and actor graph, imagine that these are actors and these are the movies that they starred in. Actors only connect to movies. They don't connect to other actors in our main graph. So that is a bipartite graph. A multipartite graph is a graph where you have multiple non-overlapping sets. So the entire movies graph that we're using is a multipartite graph. Because you can separate all these different nodes into separate, distinct, non-overlapping sets. And that's not because they're called users, actors, movies, etc. That is literally because of the way in which the relationships are structured. So removing the labels doesn't make them not multipartite. They still remain multipartite. And a heterogeneous graph is a graph that has multiple labels, multiple relationship types, and they can connect to each other. So if actors connected to actors, that would also be heterogeneous in this particular instance. And a heterogeneous graph can be multipartite. And then we will start taking a look at why PageRank matters on structure and how these structures impact you. But I think that's probably a lot to hit you with right now. So what I'm going to say is let's take a 10-minute break and we will come back and hit this now in 10 minutes. Harry, how are nodes or even relationships attributes taken into consideration? Yes, we are going to cover that. You have to intentionally project them, and you project the relationship and node attributes that you need to analyze. But we will cover that when we come back in 10 minutes. So I will see you all back here at 3 minutes past the hour. Okay, all good. I will stop screen sharing. And I will disappear momentarily. Thank you, Daryl. You too. Hello. We are not starting for another 2 minutes, but I'm back because I'm just so jazzed. So I was making a coffee because I'm a coffee drinker. And I was thinking, yeah, it's a coffee break. We're all going to go for a coffee break. And then I thought, maybe you all don't drink coffee. So if anybody drinks anything other than coffee or has a particular special brand or type of coffee or tea, or maybe you're matcha people, the matcha people, then pop it into the chat and let me know. I'm interested to know. Also, tell me where you're from. That'd be great. Questions. Mladen, that's the long break. Also, Mladen, I've said your name a bunch of times now. Can you correct me if I'm pronouncing it incorrectly? That would be fantastic. That's the long break, or later we have something longer. So later we're going to have another, I had planned for another 10-minute break. This is like an intense 0 to hero course. However, I'm happy to set up a poll for that. Who would like a longer break? I mean, at the end of the day, when we finish here, then you can go through the course in your own pace. So if everybody would prefer a longer break later, then yeah, we can make that happen. So Alex or Braun, if you could, oh no, I can set up a poll. Here we go. Type your question here. 10-minute second break. 30-minute second break. Boom. Multiple choice. A, 10 minutes, 30 minutes. Okay, this is my first poll. So if I've done it wrong, my sincerest apologies. So, Nushin, just black tea. Awesome. Do you just black tea? You don't put any lemon or anything in there, or mint, just straight up black? Fernando, I have one question not related to the course. I don't know if it's possible to answer. Is this learning platform built in-house, or do you guys use some third-party vendor? As a teacher, I find it really good. Well, thank you, Fernando. It is in-house, and we put a lot of work into it. And by we, I actually mean Adam, who runs Graph Academy, puts a lot of work into it. I would say, I mean, I'm obviously not sitting right beside him while he's doing it, but he spends an inordinate amount of time adding new features and making it awesome. One really cool feature that we've just added, actually, is if you go and you do the Neo4j Fundamentals course now, we are testing out a new AI application that will talk to you and help you to build a data model. And if you go test that for us, then that'll be really helpful, because we can kind of see feedback, see if you like it. You can thumbs up it, thumbs down it, and we can try and make it better, because what we're always trying to do is make Graph easier to understand and easier to use. So any information we can get from your end would be great. So I think we are now at 11:04, tardy. So I'm going to share my screen again. And for those of you who are wondering, because I can see the chat hopping with questions about my drink of choice, it is in fact a flat white. Because I'm a millennial, and apparently all we consume is flat whites and avocados. It's a good way to live. So, why structure matters? PageRank example. Before we move on, does anybody have any questions regarding structure? Because it seems like cool, we'll cover that later. But it is one of the most important things to understand, that there are these different structures and that they are physically different from each other, and they behave in different ways when you run algorithms on them. So don't worry about the algorithm part, but just the idea of monopartite, bipartite, multipartite, heterogeneous. Does that make sense to everybody? Do pop it in the chat. Do say yes, no. What are you talking about? Heterogeneous who? Please feel free to let me know, and I will spend a little bit more time on that. Otherwise, we will mush on. So, PageRank, we're going to cover it in a little bit more detail later, but in broad terms, it ranks nodes by their importance in the graph, and it ranks them based on incoming connections. So you've probably heard of PageRank. It is the Google algorithm. Well, it was the Google algorithm. Who knows what they're doing now? But basically, the idea was that Sergey and Larry realized that search wasn't working. And so every page in the internet is a node, and every page that links to another page is like a vote for that node. And so it recursively traverses the entire network. If you imagine like a little surfer that's surfing the web, and it goes through links and through links and through links, and then randomly teleports to other parts of the web and does it all over again. Every time it reaches the same page again, then it increases the rank of that page relative to all the other nodes. And it optimizes for quality of connection rather than critical mass of links. So you could have a load of low quality websites all linking to one website. I'm sure we've all seen this in real life. And they won't matter as much as, say, a .gov link or a .edu link that is linking to a website, because the quality matters more than the quantity in PageRank. But it's not just for labeling web pages or analyzing web pages. You can actually use it for a bunch of stuff. So, for example, I'm currently working on a Wimbledon prediction engine that, as its first layer, is using PageRank as a property. And just as an example of how powerful it is 2% on average better than ATP rankings. If anybody watches tennis, then you'll know what that means. But just as an example that it can be used in a bunch of different contexts. So PageRank ranks nodes by importance based on incoming connections from other important nodes. And now let's see what happens when we run it on our unlabeled bipartite projection. So we can just run that, and now it's going to run. And so the issue there is that should say name. Cool. So if anybody didn't catch that, just change title to name. I fear my merge has not gone into the repo. But that's okay. We will continue. So what PageRank is doing here is it is telling you which actors in this network have, in this actors graph of actors collaborating with other actors, have more or less influence. In this case, Gerard Depardieu has the most influence, and then Christopher Lee, and then John Wayne, Samuel L. Jackson, Michael Caine, Robert De Niro, Bruce Willis, Eric Roberts, Harvey Keitel, Willem Dafoe, etc., etc. Now, what's really interesting about these results, right? This graph, I made this graph. This is a massive version of our usual movies graph, which you might be familiar with, and it includes a ton of connections. And a lot of these top-ranked actors actually aren't in the standard movies graph that we use are in this one. So in the standard movies graph, when you run PageRank, you get Robert De Niro as the top link. But this actually has all of those top actors' connections. And if you go to Gerard Depardieu's IMDb, you will see that he has acted with just myriad actors. And you may not have even noticed him. He just rocks up in Hollywood movies, rocks up in other films, in European films, in British films. And he just acts with these incredible actors that you know as household names. And even if you're not particularly aware of Gerard Depardieu, you will see that he has outsized influence for his sort of household name value globally. And he's an awesome actor. Germinal, great film with Gerard Depardieu. So, in our actor-movie bipartite structure, PageRank flows into movies, but it has nowhere to go from there. And that's called a spider trap. And we're still talking about structure here. We're not talking about PageRank specifically, just to kind of reframe that. So what happens with it is, because our in-memory projection might be structured in this way, all the rank is flowing into movies, right? And none of the rank is flowing back out to the actors, which means that a lot of actors are going to have lower PageRank, right? And rank sync is another thing that can happen. So that is where you have these chains of nodes where they're all link forwarding. This won't happen in the movies graph, but it can happen in a social media graph, where all the rank is being voted this way, and then it gets stuck in a loop or a sink. And so it'll just kind of float around in there, and then they'll all just give each other rank. And so all the results will be skewed. Don't worry too much about this. It's just something for you to be aware of, that it is a problem that you need to account for. So again, we're talking about the graph structures here, not algorithms. We're just framing with algorithms so that it makes contextual sense. So don't worry about the intricacies of PageRank or anything like that. In our bipartite graph, movie nodes become rank sinks. So again, all of that rank is flowing into the movies, but not flowing back out to the actors. And that's because they receive connections, even though they are meaningfully important. Now, let's return to that second projection, the actor-to-actor collaboration graph here. And I'll just make sure that I have it in memory here. And I did not. So if you don't, make sure that you add it there. And then we will jump forward. So now this graph that we have just projected is a monopartite graph. All the actors connect to other actors. So what we've just done is we said, here's the main graph where actors connect to movies, right? And we've gotten rid of all those intermediate relationships. And we've just said actor connects to actor, actor connects to actor, and so on, back and forth, right? There's no way of separating these nodes meaningfully into non-overlapping sets. So that's what makes them monopartite. So what happens when we actually run this, we run PageRank stream on actors only, and we still get Gérard Depardieu, we still get exactly the same results, but what's not going to happen here is we're not going to poison our results with the movies. And for example, if you had reversed those relationships or you tried to do it in another way, you might end up with all actors being 0. So bear in mind that the projection that we've projected still does not have any labels on any of the nodes. So it's recognized that Gérard Depardieu is the most influential actor in the network, even though Gérard Depardieu is not named in the graph. It's just that the node that represents Gérard Depardieu is the most influential node in that network. It is the structure and not the labels. So the example that I've given here is you've got your movies graph data model here, right? Which is exactly the same model as a model here where you might have cards connecting to users, IP device connecting to users, and users connecting to fraud risks, right? It's identical. It's the same model. So these are going to behave the same way. But let's say we have another movies graph that we've modeled a little differently, where we said genres contain users, because say we've identified these users like genres. Directors contain users. Directors work in genre. Let's say this is now our new structure. We've got identical labels to our movies data model. And yet, when you run PageRank on this exact model, it's going to have a completely different behavior because the structure of it is completely different. And that's what we really need to understand, is that our projections of our graph models matter as much as the algorithms we're using to analyze them. Because you could run this algorithm on the wrong projection and it'll run. It's not going to error. It's going to give you results. It's just that those results will be meaningless. So for some algorithms, you will want to retain node labels. And we use our configuration map here to retain those node labels. So just like our normal projection, we have our match, and then we call gds.graph.project, and then we name our graph, get our source and our target, and then we get our source node labels, and we say we want to bring in our labels source. And all that's going to say is that anything we've said as a source, I want you to bring those labels into the projection. And then target node labels target, and relationship type R, which is the R or as we say in Ireland, and type or here. And that's just going to get that relationship type and bring that into the projection with you. So we run that now. Now, actors, movies labeled is a bipartite projection that has retained the labels. So you want to preserve the labels when you need to filter algorithms by node type. We're not going to do that today, but that's a really good thing to remember. Node type distinctions affect, and when node type distinctions affect your analysis, it's often not going to be the case. So normally you're not going to need node labels, but there might be specific situations where you do. And generally just use the default unlabeled when you're projecting a true monopartite or bipartite subgraph, in which case it's going to behave the way it behaves and it doesn't really matter. Or the algorithm ignores node labels, which most do. So as an example, again, remember, we are talking about structure, not algorithms here. So do not worry about knowing node similarity in any depth. Node similarity is an algorithm that compares nodes based on their shared neighbors. So it works best on graphs that can be separated into distinct sets of nodes, specifically bipartite graphs. There is an argument to be made that you can use it on multipartite graphs in certain circumstances, but just for now, just accept and have it as a rule in your head that node similarity equals bipartite graph. And if you are running it on something that is not bipartite, then it is wrong. And even though that's not totally true, just stay with me and for the moment, assume that it is. So the following projection will create a bipartite graph with preserved labels of users rating movies. We're going to call it user rated movie. We're going to bring in our source and our target, and we're going to keep our node labels, right? And we can just run that, and that's done. And we can see that we have 26,000 nodes and, well, 27 if we want to be specific, and 43,000 relationships. Now we can run node similarity on that graph, which again, all we're doing here is we are running node similar call GDS algorithm name, which is node similarity in camel case, and then stream, so mode. So we're saying with stream, do not write anything to my main graph. All I want you to do is give me the results as a data frame, and then we're yielding all those results. And don't worry too much about these for now. And then let me just close this. Oh yeah, there we go. And so what this has done is it's told us that Ikena Bianco has watched exactly the same movies as Bimpe Sandoval. So they get a similarity 1, right? And this is done every single user in the database. There are 100,000 users who have watched tens of thousands of movies, and they've all watched different movies. And these are the top rated ones who have watched the same movies. If we were to filter this down, then we could say who've not watched all the same movies, and we get users with a similarity of like 0.8, and we'd say, right, these 2 users have watched a bunch of similar movies, but here are the movies that they don't overlap on. So maybe this user would like to watch the movies that this user has watched, but they haven't. And so that's like the basis for collaborative filtering for recommendations. And you can see how quickly that ran. Even though it is actually a pretty complex algorithm, and it does take a lot of computation on large graphs. That's in terms of Neo4j and graph generally, in comparison to other algorithms, but actually it's still super quick for what it's doing. Imagine trying to run that in relational. It just you'd be waiting forever. So node similarity finds users who rated similar movies, creating new user-to-user relationships. So that is actually what it's doing. Let's say this is a user, this is a movie. This user has watched these movies, and this user has watched these movies. So these 2 users have watched 2 of the same movies, and so they are considered similar because they overlap. Now, it is doing that for every single user in the database in one run of the algorithm. That is huge. So, quick reference, choosing your graph projections and your structure. PageRank and betweenness. We will get to betweenness a little bit later, but they work best on monopartite graphs. You project a single node type, right? Now, you don't have to do it that way, but often in your graph, node types, so node labels and structure will kind of be the same thing, but they're not technically. They are different. But it's a good sort of heuristic way of thinking of it is, I want to know who are the most influential actors. I therefore don't care about movies. I only care about actors, so I'm going to project a monopartite graph of actors and only actors. Node similarity, it's designed essentially for bipartite graphs. So that is what you need. And then community detection, which again we're going to cover shortly, varies by the algorithm. It really depends on what style of community detection you're using. But you can use it on heterogeneous graphs if you want to cluster like certain node types with other node types and you don't really care for your question about whether they're different types. Or in some cases, you might just want a monopartite or a bipartite. It really depends on your use case. As I said earlier, these are playbooks. They're not, it's not like 1 + 1 = 2. It's more like 1 × 1 = imaginary minus 7 = what is it you're trying to do again? So common terminology, just to recap that, we have monopartite graphs, nodes that cannot be separated into distinct non-overlapping sets. Bipartite graphs, exactly 2 non-overlapping node sets, so the movie actor bipartite graph. Connections only between the sets, not between the nodes in the sets. Multipartite is the same, it's just more sets. Heterogeneous, multiple node types and or relationship types, they can overlap. It's cool. It's the guy who shows up to the party late and is like, yeah, whatever. Oh, hey, why don't we like do this thing that wasn't planned for the party? Unlabeled, GDS doesn't know the node or relationship types by default. You're going to have to configure that in algorithms. Okay, let's progress. How are we doing on time? 11:23. Okay, cool. So this is a practice section. Because we lost a little bit of time in the beginning, I'm not going to get you guys to practice too much on this. This is quite a long practice session, so I am going to skip this. But I would, in your own time, suggest that you go through this and practice these yourself. So all this is going to do is if you go into slide view, you will practice everything that we just discussed. And it's going to give you questions. So run PageRank, and it's going to ask you to do this on your own without any help. And then it's going to give you some explanatory information afterwards. But for now, let's move on through the crystal maze to applying algorithms. So we have just discussed algorithms in the context of projections, or rather projections in the context of algorithms. Now we're going to talk about the algorithms themselves and what they actually do. So as we discussed before, you've got centrality, you've got community detection, pathfinding, similarity, and node embeddings. We've discussed a few of these at length already, so we won't spend too long on them. Again, don't worry too much about the specifics of each algorithm. Later in the course, you're going to use them yourself. So first, let's create an actor collaboration network. So this is the one that we've already run. This is just the actors connected to actors, and we're ripping out the movies, so we just have that monopartite network. Now, on this network, we're going to run centrality. Centrality algorithms, they rank nodes by importance, but importance depends on how you define it. That's why we have multiple different algorithms. So in this example, we have PageRank, which is ranking based on those incoming relationships, so votes from other nodes in the network. Centrality, which is ranking based on outgoing relationships. So how many nodes do I connect to? And betweenness is calculating. It's very, very interesting one, and it's one of the most useful algorithms in graph data science generally. Betweenness tells you which nodes are most important in terms of their influence, which is, let's unpack that for a second. What it's really doing is it's saying, for every single node in my graph, I want to get the shortest path from that node to every other node in the graph, right? So you can see this kind of blows up in terms of computational complexity. So it can take a while to run, especially on large graphs. There are ways around that. But it's finding all those shortest paths. And then what it's doing is, for every single time any node shows up on that shortest path, it gets a point and its score increases. And at the end, it says, right, how many times did every node show up on a shortest path for any other node to any other node? And really, if you imagine that you have a graph on this side and another graph on this side, and then one relationship to an intermediate node connecting them, even though that node in the middle has only two relationships connecting it, that will have the highest betweenness in the graph because it is on the shortest path between every other node in those two components, because they have to go through that bottleneck. The reason why it's super useful is if you're running a graph on a service network or logistics or anything like that, you can immediately see where your bottlenecks are. So you can have this huge complex logistics graph and you're like, oh, I don't know how to go through it. I don't know, where are my bottlenecks? Where are my failure points? And you can run between this and go, oh, here they are. These are my failure points. And then you can actually do something with that information. So, for example, again, we can run degree. So gds.degree.stream, actor network, and we run it. And on our actor-to-actor collaboration graph, we're getting slightly different results than we were getting on our bipartite. We're getting John Wayne at the top and then Gérard Depardieu. And that is because John Wayne has been in more movies than Gérard Depardieu, which is interesting. It's a good way of looking at the difference between PageRank and degree centrality, actually, because Gérard Depardieu is more important than John Wayne, according to PageRank, but John Wayne has been in more movies. So then if we run PageRank on the same graph, here we see Gérard Depardieu and Christopher Lee, and John Wayne is in third. And that is because even though John Wayne has, according to degree centrality, starred in more movies, Gérard Depardieu has starred in more influential movies and has acted with more influential people. And so has Christopher Lee. And then betweenness.stream. So we're going to try and run this. This should be fun. It may or may not run in time on this graph, but I think we've got the idea of betweenness and what it does. All it's going to do is return, again, results like this, but it's going to tell you which actors have the highest betweenness. So if you run that, feel free to go and run it. You'll still be able to run other queries in the background. Just let it run and then come back later and take a look at the results. So same graph, 3 centrality algorithms, and each of those 3 algorithms gives us a different answer, a different version of centrality. So the algorithm that you choose and the modeling of the projection tells you and defines what importance actually means. Community detection finds clusters, so nodes that are more important to each other than to the rest of the network. Louvain groups nodes by maximizing what's called modularity. So modularity is essentially how interconnected each community cluster is to itself in comparison to its connections going out from that cluster to other clusters, which are also more densely clustered. And modularity is the number that you use to understand how modular those networks are. So if we run Louvain on our network, then what we get is a community ID and the size of that community. Right now, this might look a little bit abstract right now, but in a moment, if I remember correctly, I have set up a query to make this a little bit more interpretable. But you have a community that is called 7504, and that label is on that community now. And in that community, there are 7,724 actors, right? And they exist only in that community. They exist in no other community. That is their community. That is where they live. So let's see who's in the largest community. We'll run stream again. And here we get back our results. So in community 7504, we have Timothy Spall, Colin Meaney, Henry Goodman, Michael Sheen, Maria Bello, Sean Beam, blah, blah, blah. And community 7504 has 7,953 actors in it. Then we have community 1075. And then we get another bunch of people. So we get Frank Sinatra, Clint Walker, Dick Martin, and suddenly we start seeing a theme emerge. These are all actors who are from a very similar period of time. But remember that some of these actors will have worked with some of these actors. I know for a fact Timothy Spall has acted with actors from this time period as well, because he's been going for donkey's years. But Louvain has managed to separate them into separate communities and said, yes, okay, these people are connected to each other, but actually the connections from within this modular community are more important. So we're going to put them in, we're going to label them as being one defined community, and we're going to put these other people in this other one. So if we go over here, Louvain builds hierarchical communities. So you can run your stats here and you can see what the modularity is. So we've got a modularity of 62 or 0.62. So that's basically modularity is between 0.0 and 1. And anything over 40 or 42 is pretty good. That's not just a Hitchhiker's reference. That actually is genuine. So maybe, maybe Douglas Adams was onto something. But that 62 is pretty good for our actors network. But remember, over here, we have configured it to run with only one max level. So that is how many times the algorithm will iterate over the graph and cluster things together and try again and try again and try again and try again. And each one of those try agains is a level. So if we do max levels 5, we can run. And we get a higher modularity score, 65. So now we see that actually allowing it to run longer, it does actually converge. And we get 65 modularity, which is higher than 62, which means that all of our communities in the aggregate, they all have their own individual modularity scores. But in aggregate, the graph in general has a modularity of 0.65. And later on in the course, you will see examples of that. So node similarity, as we explained, finds nodes with similar connection patterns. And again, we can project that user-rated movie graph, run node similarity, and it will return to us which users are most similar. And out of interest, let's see if betweenness is done. And betweenness is done. So earlier on, we ran the betweenness centrality algorithm. And what we have found is Toshiro Mifune is the highest betweenness person. Now, I've actually never heard of Toshiro. However, the reason why he would be the highest is because they exist on a bottleneck between other actors. So you might find that Toshiro has been in a bunch of movies with other famous actors whose names you might know, or has worked with like a small crew of people you've never heard of, and they exist between others. So they'd have quite high betweenness as well, but they also have to pass through Toshiro. And then you have Anupam Kher, Om Puri, and that will go on down the list. So let's continue on our journey through algorithms. Pathfinding algorithms, they are just finding the shortest path from, or not necessarily the shortest path, but Dijkstra's will find the shortest path from node A to node B. And in this particular case, we're demonstrating Yen's shortest path, which finds multiple shortest paths. So you'll see here that the red path is finding this path here, and the blue path is finding this path here, and it will find parallel sections of paths. So you can get like really quite granular with it. So Dijkstra's, for example, will find the shortest path between two nodes. It's Dijkstra's, not Dijkstra. That is a typo. So let's see if we can find the shortest path in our actor graph between Kevin Bacon and Meg Ryan. And again, we're just doing gds.shortest path Dijkstra's.stream. Actor network, and the shortest path is Kevin Bacon acted with Jennifer Jason Leigh, who acted with Meg Ryan, and we can change these. So let's say let's try Charlie Chaplin, and the shortest path between Kevin Bacon and Charlie Chaplin is Kevin Bacon acted with Ileana Douglas, who acted with Claire Bloom, who acted with Charlie Chaplin, and they are of course a million years apart from each other. And that was done in 95 milliseconds. node embeddings is our last category that we're going to talk about. Node embeddings, as we discussed earlier, will turn your graph nodes into vector representations of their position in the network. So you can see here from the gradients what they're kind of doing. So you've got like a green node here, which is creating its vector by propagating out into this green node here, which propagates out to this sort of orangey yellow node here, which propagates out to this orange one. And then it will create that vector to get the proximity so that when you get, let's say you run a similarity check, when you run node is similar to node, they'll be similar because they're actually close structurally in the graph, positionally. There is some nuance to that, but we're not going to cover that in great detail because, as I said, that's a whole other course. But we will show you how to use them later on. Let's take a look at our time. 11:37. Lovely. Okay, we're good. We're good. Boom, boom, boom. So one of the algorithms and one of my favorite node embedding algorithms, in fact, one of my favorite algorithms of all time, I think I'm a little bit unhealthily obsessed with this algorithm, is FastRP. So FastRP, fast random, it stands for fast random projection, and it creates those vector representations. Broad overview, what it does by default is it's going to get the proximity. So it's going to tell you which nodes are closest to other nodes in the graph. You might think that that's not a huge deal, but actually that's a huge deal, because let's say you want to do GraphRag and you're using semantic vectors to find out which paragraphs are semantically closest to other paragraphs. That's fine. But, you know, two paragraphs can be semantically close and actually the connection between them is completely spurious because they use similar words or similar phrasings. And that's, you know, vector search is good, but it's not perfect. Using something like FastRP, if you're pulling out like mentions the same thing in a knowledge graph, and then you embed those nodes, now you're finding nodes that are actually structurally, informationally, hierarchically similar to each other. You can make a similarity graph out of that in the same way that you would make one out of vectors, semantic vectors, and now you can use that in your GraphRag. And even better than that, even cooler than that, our implementation of FastRP, which is not the norm, allows you to add property features. So what you can do is you can take your wonderful semantic vector and a bunch of other outputs from other algorithms. You can shove them into FastRP, and you can generate a vector that actually encodes all of that information in one vector and use that as your similarity graph. And so now you're getting tons of different dimensionality across the graph. That's kind of the broad overview. I could talk about it all day, but I'm not going to. So again, even though we're doing all this complicated stuff, it's the same. It's call GDS dot algorithm name FastRP dot stream mutate write stats. Name the graph that you want it to run on in memory. In this case, you want to configure in this configuration map the embedding dimension. So we've put 64, but you can put whatever you like. And then yield the node ID and return those results. Obviously, we're not going to return the entire vector, but Timothy Spall, here is Timothy Spall's vector. There you go. That's his position in the graph as a number. You can now use these in machine learning. You can use them directly with similarity graphs, GraphRag, blah, blah, blah. The world is your oyster. So let's see if we can find actors who are structurally similar to Kevin Bacon. And we just embedded using FastRP stream on our actor network. And the most structurally similar is Josh Brolin, then Tommy Lee Jones, then Marisa Tomei, Josh Lucas. And if you check these out on IMDb, you will find that they are in fact similar in terms of their collaborations. Ed Harris, Brad Pitt. You could do this for any actor in the graph. So let's drop our projections before we move on. And let us progress. So, actually, I think I missed one thing there, didn't I? Oh, yeah, that was just the recap. I think we're good on that. So, can everybody we'll just take 2 minutes now for everybody to kind of put questions in the chat because it's all gone a bit silent. And I want to know, are you silent because you're intently engaged? Are you silent because you've gone, I'm done with this? Or do you have questions that you're afraid to ask? Because do ask questions. There is no such thing as a stupid question. And I see that they're in the Q&A here. Lovely. So, Rishikesh, is there a use case or example where we use graph on graph, multi-layer graph DB? Is it good or bad? If yes, is it covered in any training program by Neo4j? We don't have a training program about that, but that's a good shout. Are there use cases where we use graph on graph? I mean, yeah and no. I guess it kind of depends. Graph is incredibly flexible. So yeah, I mean, I don't want to say no, but you can have a gigantic graph and then you can project your subgraph as we've been doing. So you have your graph of movies, actors, whatever, and then you project your subgraph from that to run algorithms on that subgraph, and then you write that back to your big graph. Generally, the more connected a graph is, the better. So the answer is yes, but I would layer the graph. You do that in the modeling phase. But in saying that, in theory, yeah, you could have multiple different graphs. If you really wanted to. It's just that you're then going to struggle to find those connections that Neo4j is really good at finding, because they're disconnected by definition. So yes, layer graphs. Put as many layers of graphs into your graph as you want, but just make sure that they're modeled in a way that makes sense. Akil Nair used sentence transformer for data embeddings and stored as a property on node while fetching data into graph, and later used cosine similarity algorithm for match find using that property. Want to know if that can be done better to create data embeddings in Neo4j itself while putting data into graph, or should that be done after data is populated into the graph? If so, how? Or is this node embeddings going to be helpful there? Right. That's a huge question. I'm going to try and answer it as in the way that I understand it was phrased. Can I have a little sip of Go juice first? So, in Neo4j, you can use our Gen AI features. So you've got a Gen AI plugin in desktop, and in Aura it's already pre-installed. Let me see if I can get you the docs. Gen AI plugin Neo4j. Yes. Kablamo. Okay. I just posted that there. I'm going to post it in the chat as well. There you go. So you can use that to generate embeddings using Vertex AI or OpenAI directly through Neo4j. So you don't actually have to do that outside Neo4j at all. But yeah, you can just add those embeddings to Neo4j as properties as well. And then you create a vector index in Neo4j. We're not going to cover that today. That's a different sort of topic outside the scope. But yes, you can do that in either way. Excuse me. You can do that in any way that works for you. Does it already get included in the projection? No, you have to project properties. So if you want to do similarity, you have to project the embedding into your projection, and then you run the algorithm using those properties. If the criteria matches, or should we drop and recreate the projection? So if you are creating the embeddings inside a projection, which is different. So the only way you would do that is if you're creating node embeddings, which are different from semantic embeddings. Then you can mutate the embeddings onto your projection, and then they stay in your projection, and then you can write them back. But if you've written them to the main graph, then yes, there's another way of doing it, but really, yeah, the easiest way is to just create a new projection with the properties in there. I hope that has answered your question, and let me know if it hasn't. Judith, related to my previous question on yield, here attributes, community ID, modularity are specific to the algorithm you use and cannot be used for. Yes. So in the GDS documentation, we will cover this in more detail later, but just in case we don't reach it, let me give you an example. So in the GDS documentation, and I will link you to this. I'm actually going to pop that in the chat. Yeah. So in the GDS documentation, you can see for each mode what you're able to add and how you're able to configure it. So whenever you're creating an algorithm or you're running an algorithm, you just go to the algorithm that you're running, probably have one here, and you add it into this configuration map here. So it's called gds.algorithm.mode, and then title of graph, configuration map, and you're going to get that configuration from here. They are different for every algorithm, yes. There are some that are kind of universal-ish, like concurrency. So how many threads you're going to run the algorithm on. Default is usually 4. But yeah, for the most part, you really want to study what configuration options you have per algorithm. And there are a ton of algorithms. So that is, we're coming up with courses to deal with each algorithm separately. So if you have a particular one and you're like, oh, I want to use that, you will just be able to jump into Graph Academy and use those. They don't currently exist. I am working on them. So I think that answers your question. Fatima, does FastRP work for heterogeneous directed graphs? FastRP works on every graph. However, most algorithms work on every graph. That's not the thing we have to be careful of, because if it doesn't work, then you'll get an error and you'll go, oh, cool, that doesn't work. The thing you need to be really careful of is not using a graph on a graph, not using an algorithm on a graph where it produces an output, but actually your modeling has been poorly, you've poorly modeled the graph. And so the results are not actually telling you what you think they're telling you. So for example, I had a funny image for this actually. Let me see. No, I've gotten rid of it. Okay, I will explain with words and flailing hands. FastRP will find the structurally most proximal node, right? And this is true of other algorithms as well. If you have a graph where man owns dog, dog likes dog food, man likes steak, and man likes dog, right? And dog likes man. What's going to happen is you're using that for recommendations, and you just run FastRP or you run node similarity because someone told you that it works for recommendations, and you just kind of mindlessly run it. Then what you're going to end up doing is recommending dog food to man. Which, who knows? Look, no judgment. If you like eating dog food, I mean, you know, some of it's pretty posh these days. Maybe that's actually a legit recommendation. But that is not an algorithm problem. That is a modeling problem. And the algorithm will run. And it's the kind of thing that you might not see if you run the algorithm on millions of nodes and most of them kind of look legit and it looks like they're good recommendations, even though they're not. They're not good recommendations. They're actually bad recommendations. But somewhere in there, you've got like lower down nodes that are recommending dog food to people. That has poisoned your entire usage of the algorithm. This is why we're spending so much time in the modeling of projections, because it is simply the single most important thing that you can master. And I wouldn't even put myself in the mastery category of this. I make mistakes in this all the time. So yes, it does work, but it's not about whether it works. It's about whether it works for the question that you're trying to answer. What embedding model is used for the FastRP algorithm? So FastRP is the embedding model. So it's not, again, Jan, it is not embedding the text. That's not what it does. It is embedding the actual node position within the network. So FastRP is the thing that is embedding. There's no like OpenAI model, all MP, net, blah, 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 none of that stuff. It is FastRP that does it. Again, we can't spend too much time on it, but I highly suggest that you go and read the paper. And the paper is pretty involved. It is actually, if you go to node embeddings, go to FastRP. I think we've got a link to it in here. Yeah, it'll be in here somewhere, but there is a paper for FastRP. Read that paper, or better yet, chuck it into Claude and ask Claude to read the paper for you, because it's very involved and it's a lot of sort of dense language to describe a concept that's actually relatively simple in visualization terms. So for now, let's go back to our course and we'll have a look at our execution modes. Now, I think we've pretty much covered these, but I just want to go over them again in this format, just so we're really, really like dead clear on what they do. So you've got your projection here. PageRank mutates your projection. PageRank write writes directly to your main graph. PageRank stream creates a data frame. PageRank stats creates a data frame of the stats. So you got a data frame of stats and a data frame of results. And then PageRank.mode, right? So you can put mode, stats, stream, mutate, write, dot estimate. So it's an extra appendage. That then gives you a data frame telling you how much memory you're going to need to run an algorithm. And then, Harry, you just asked a really good question, so I am going to answer that. Are projections a generally good way to fix poor modeling and get it where it needs to be for an algorithm? No, is the short answer to that. Like, yes, you could do that, absolutely. But it's like, let's say I have a broken bike that only has one wheel, and then I say, oh yeah, but like, if I just get an axe, I can chop off the back of the bike and turn it into a unicycle, and then I can use that unicycle to get from A to B. And it's like, yeah, you could do that. Yeah, that's like a legit thing you could do. It's like also the worst way of doing it. So no, you want to make sure that your model, your basic graph model, actually makes sense in general, and so that it's easy to make the projections. So like, you really shouldn't be doing heavy remodeling for projections. You want that to be as simple as possible. And if you find yourself doing that, it's time for a refactor. But in saying that, Neo4j is awesome for refactoring. You can just refactor stuff in the blink of an eye. So I wouldn't worry too much about that. I think a lot of people get stuck on import and modeling. Just do it, make mistakes, see what happens. Eventually, it will click. So the 5 execution modes: stream returns the results, stats, summary statistics, mutate stores results in the projection, write persists results to your database, and estimate checks the memory requirements. So all algorithms follow the same pattern. It is call gds.algorithm.mode. Then you give your graph name. That is the name that you are going to call your graph. And the only reason why that exists is so that if you have multiple graphs in memory, you're able to direct GDS to run an algorithm on whichever one you want. And then the optional configuration map. So that is all of these things that we were talking about before in the docs, which I have inexplicably gotten rid of. But yeah, so you'll put all your configuration settings in there and you'll yield the results, and then you can return whatever you want from the yielded results. So we can project this graph here, as we have been doing. I won't spend too much time on that. We've projected it a ton of times. It's the same one. And again, here we're running gds.pagerank.stream, and we're just streaming the results. It's exactly what we did before. It's just instead of looking at PageRank, we're now looking at stream. You can use this to explore results before deciding whether or not you want to store them. You can run one-off analyses. You can feed these results into other Cypher operations, and you can export to CSV, pandas, etc. via the Python driver. Really good for exploration, and especially if you don't want to persist results anywhere, you just kind of want to see what's up. Stats mode runs the algorithm in full. It does actually run it, but it'll give you stats. So again, it's exactly the same. We're running Louvain here with stats mode, and all it's giving us is the community count and the modularity and the RAN levels. Now, I'm returning and yielding. You don't actually have to do that. So I can do stats without that, and I can get this huge map that gives me modularity, individual modularities, the levels run, the community count, the community distribution, milliseconds, blah, blah, blah. And that's what I'm returning here. So I'm yielding those fields, and then I'm returning those fields. But if you don't actually specify, you can just get them all. To be honest, this is what I usually do because I'm lazy. And so here you've got your modularity, then you've got your individual modularities for communities, so you can kind of see the skew. You get community size distribution here, so how big like the biggest community is versus the median community and so on. So that can be really useful. So yeah, you can get all of this into a data frame. You can use this in multiple ways then afterwards, even write it to a different data store if that's something you wanted to do. Oh yeah, sorry, but the main reason why you want to use this stats is you might have a configuration that is suboptimal, right? And using stats allows you to reconfigure the algorithm until you get the stats that you're looking for. And that is the main reason to run it. Because if you're constantly running write operations and then checking the results of the write operations, I mean, not only is that a ton of I/O, but like you're just, it just becomes a headache, because then you end up with Leiden V1, Leiden V1 final, Leiden final V2. And I've been in that situation, and that's not something you want. So, this lets you kind of plan for that. Good for understanding overall algorithm behavior, testing configurations, yada, yada, yada. You get the point. Then PageRank.mutate. Again, as I said, really want to drill this in. That is not changing your main graph. That is changing the graph that you have in the projection. And that is it. You can then write those results later if you want to, or you can drop the graph and disappear them like they never existed. But it's great for chaining multiple results together and just working in the algorithm until you're done. And then write will persist those results into the database, into your main graph. And that's good if you know, like, let's say you want to update a bunch of stuff, or you're running in Python, you're running an app, and you kind of want to, you got another app that needs to take things from Neo4j or whatever. You can just rerun the algorithm, rewrite the results. It'll replace the old results. It's not going to write like a new version. It's just going to overwrite what's there, which is again why you need to be very careful with it. And then you can grab those from another application, or you can then use them and reproject them in another way, or you can turn those into nodes. Let's not go there. That's a whole other kettle of fish. And then estimate is again gds.pagerank.write.estimate. So you're adding that as an extra at the end. For most use cases, like smaller use cases, smaller graphs, you probably don't need to do this. However, sometimes you will find yourself with a massive graph, or a graph on which you need to run an extremely expensive computation, like betweenness centrality, which we saw earlier, is crazy expensive. So just make sure that if you're going to run something like that, run estimate before you run anything else. And we can run that there. Oh, we already did. Okay. Yeah, so planning before running expensive algorithms, checking if your heap can handle the operation, and deciding whether to sample or run on the full graph. So there you go. An example workflow might be estimate to check the memory requirements. Stats, I always run stats first on certain algorithms like community detection, because you kind of have to get a sense of what's going to happen first before you run it for real. Stream to explore specific results. Then mutate to get those results into the projection and run them together, and then write if you're just writing like one particular result to your main graph. You're never really going to use all 5 in a row. You'll probably default to 1, and depending on how you feel about them, I think it's kind of personal preference. You might just pick one. So yeah, configuration map. Most algorithms accept a configuration map like we have here. So in PageRank, for example, we have max iterations and damping factor. So if we copy this, and now we run PageRank.stream with those configuration settings, now we are getting, oh yeah, we haven't returned the results. Anyway, the results here are different to what we would get. So you can even see here that the top person has a lower page rank than Gerard Depardieu did in the previous one. And that is because we've increased the damping factor, and we've also increased the max iterations. So max iterations by default is 10. Damping factor by default is 0.85. And damping factor is basically just a control of, remember we were talking about the random surfer, how often that surfer is going to teleport around the graph and restart the calculation. Available across most algorithms are concurrency, node labels, and relationship types. And node types and node labels and things like that. But yeah, for each algorithm, check out the configuration settings in the Neo4j GDS docs, because otherwise you just won't know how the algorithm works, and you should. And I use them every day. I don't remember all the configuration settings of every single algorithm. In fact, I don't even remember all the algorithms that we have. Sometimes it is just an exploration exercise. You go through the algorithms and you go, oh, that solves my problem. So yeah, each algorithm will have its own unique parameters, as we said. So a configuration strategy could be start with your defaults and run stats to test how the defaults are working out, and then run a bunch of different configurations in stats. And then once you've done that and you've got something you're happy with in stats, then run the algorithm for real. All right. And our final lesson in this module is projection configuration for algorithms, because we have some other configuration options that we can use. I'm just going to quickly jump into the Q&A and see how we're doing here. Heterogeneous directed graphs. Fatima, I answered that. Jan, I answered that. Jan, just confirming it was clear. Awesome. Thank you. All right. I'm glad that helped. So let's jump straight into projection configuration for algorithms. This sounds like exactly what we've just covered, except it's not. It's different. So some algorithms need different configurations to work correctly or to work at all. And that's what we're going to go through now. So as we mentioned, you've got directed, undirected, and weighted. So we briefly covered this at the beginning. Now we're going to cover this in a little bit more detail. Directed makes sense when direction has real meaning. So customer purchased product is a direction. You kind of want to have your relationships as verbs, which if any of you have done Neo4j fundamentals, and you should have, then you want to have verbs on their own as much as possible in your relationships. And that kind of implicitly gives you the forward direction of the subject verb object. So customer purchased product, not product was purchased by customer. And so that directionality has real meaning. So when you are weighting algorithms or using directed graphs, that directionality is in some cases going to change how the graph operates on that projection. So directed also makes sense when you want to distinguish incoming from outgoing connections. So degree centrality, I said earlier, it counts outgoing connections. So if you have outgoing connections, customer purchase product, then you're going to get the count of how many products each customer purchased as a degree metric. But if you had product purchased customer or product was purchased by customer, now that directionality has changed. So on that graph, now you're not going to get that degree for customers. You're going to see how many customers bought a product, which is useful, don't get me wrong, but it's a different thing. And this is what I mean about the structure being important, because the output that you get from running exactly the same algorithm on almost exactly the same graph is completely different. And Harry there, you're asking me, so projections are accessible to Python? Yes, they are. So that's what the notebooks are for later on. Unfortunately, due to the time at the beginning, I'm not sure we're going to hit that in time. I am going to try and make it. But for now, let's just see how we do on this, and we'll get through as quick as possible. But the notebooks are available to you in perpetuity, and they're pretty well explained, I think. So you can feel free to play around with them. So yeah, check the documentation header for each algorithm. So you got Leiden, for example, cannot run on a directed graph. It has to run on an undirected graph. And then you've got all these other configurations here that you need to bear in mind. So you need to check that header. To make a projection undirected, add undirected relationship types. So we run that. Now, this can trip people up, so I'm just going to really highlight it here for you. Undirected relationship types goes in its own config map after the first config map. you have to have that first config map represented, or the second one won't be picked up, and it will error. So if you ever find yourself trying to do this and getting an error, just make sure that you're remembering to add this first placeholder config, even if you're not going to add node labels or relationship types in. So we have now projected that. And now let's project the same data as an undirected graph, or as a directed graph, rather. Now, let's run degree centrality on both directed and undirected projections to compare the results. So if we run degree centrality there, we get Gérard Depardieu. And if we run degree on our undirected graph, oh, what do you know? It's Gérard Depardieu. Both of the versions seem to return the same results. However, let's look what happens if we only count the degree count for the movies in each projection. Because remember, this isn't the actor-actor collaboration network we've projected, it's the actor-movie bipartite graph. So if we run the directed graph, movies have received 0 score in the directed graph. And that is because they have no outgoing relationships. But if we run on undirected, movies do. Now remember, this is an identical graph. It's still bipartite. It's just the difference between directed and undirected. The reason is, in Neo4j, undirected does in practice mean undirected, but in reality what you're doing is you're creating an extra relationship temporarily. So actually it's more like bidirectional than undirected. And so you get outgoing this way and you get outgoing that way. And so you can count on both movies and actors. So if you have a bipartite graph, multipartite graph, and it's all directional, but you just want to know how connected everything is generally, then you want to project undirected. For symmetrical graphs, like the actor collaboration graph, so actor connects to actor, remember that the actors in that graph already have bidirectional relationships. So making it undirected now actually just creates 4 relationships instead of the 2, because you've already got the undirected nature of that relationship. So let's jump ahead. Direction versus projection direction. So projection level direction. Oh yeah. So basically there's one kind of scenario where you're going to have undirected relationships that are specified when you are projecting. And then in certain algorithms, like degree centrality, you can actually change and modify how the algorithm treats the directionality that you have already in the graph. So on our actor movie directed graph, we've now actor acted in movie, and we don't have movie backwards to actor, okay? There's only one relationship. And orientation natural in our config map for degree, if we just run that, then we get, as expected, Gérard Depardieu, Eric Roberts, blah, 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 the results that we all know and love. However, remember that when we ran this on the directed graph with just basic degree centrality, we got 0 for movies. Now, if we run it with reverse in orientation in the config for the algorithm, we actually get the degrees back from the reverse, even though the projection itself is still directional. So yeah, the issue with that is, if you try to run this on the undirected projection, right, you're going to get the exact same results for both. Because remember, all you're doing is swapping the relationships. So you're just reversing them. And so you actually ultimately get exactly the same results regardless. So just bear that in mind if you think like the problem is reverse direction. Not all connections are equal. Weights let algorithms treat some relationships as stronger than others. So for example, the example we gave earlier with Cheeksters, finding the shortest path. This is the shortest path in reality in this example. However, if all of those were weighted 5, 2, so on, then actually it would take this longer path nominally in terms of the actual hop count, but it is cheaper in terms of the weights. So that can be really useful in a lot of cases. To add weights, you have to add properties. And this is really the crux of what we're doing here. And this goes back to a lot of Harry's questions and a lot of other people's questions earlier. Let's say we project source user rated target movie. So we've got our user movie bipartite graph from before. What we've done here is we have added undirected relationship types here. And we've also, in the first config map above that, added relationship properties. And then we've specified R, which is the relationship variable. And then we've said the rating that the property I want you to project onto that relationship in the projection is dot rating. So now we can use this rating. I don't know why I'm pointing with my hand. You can't see it. We can use this rating to, in some algorithms, to make them behave differently. So in Leiden, which is another community detection algorithm, we can specify the relationship weight property, right? And it's rating, because it's rating in our graph. And so if we run that, now Leiden is going to do community detection. And it's going to create those communities with this rating property, acting like extra relationships are pulling certain nodes closer together than others. And unweighted versus weighted communities. So for example, you might have this graph here, this very simple graph where they're unweighted and all of these users are clearly within the same community. But now let's look what happened when we increase the weight here, or decrease, or change the weights whatsoever. These might get clustered together and these might get clustered together separately because that intermediary rel is causing a problem. So that's how it can affect you or affect your algorithm. So different algorithms interpret weights differently. Your community detection algorithm will take your properties at, say, a higher number, and it's going to pull them closer together. But your pathfinding algorithms in general are going to, not always, but in general, like Dijkstra's and Jens, they're going to interpret that high number as a cost. So they're going to try and choose the lowest number. And similarity, higher weights equal higher similarity, which is similar to community detection. And sometimes you need node attributes, so node properties, not just the connections. So you can add those in too. It's slightly different. In this case, instead of specifying relationship properties, you'll specify source node properties. Again, it's in that first config map. Source node properties, source, start year, IMDb rating, target node properties. And again, you're just getting source movie, target movie in this particular movie only graph. And we just pop that in there. And that has now projected the start year and the IMDb rating into our graph. And so now, use coalesce to provide defaults when properties might be missing. The problem is a lot of algorithms, when you project, a lot of algorithms require every single one of your nodes in that algorithm it requires every single one of your nodes in that algorithm to have the property specified, right? So you can go through all this work, and this happens all the time. So just please do try to remember this, because it's like, if it happens to you, that's fine. It happens to me all the time. But you do try to remember it, because when it happens to you, it can be quite frustrating, and you can go, oh, what? Why? I did everything correctly. And then you spend ages going through the docs, only to remember that you forgot to do defaults. So not every single node is going to have this particular property that you want. And that can be because of data import issues. It can be because of data quality issues, data cleaning. Maybe you accidentally removed it. There could be multiple problems. Maybe you wrote a PageRank property, but you didn't include some nodes in your projection when doing it, so they never got a property. Multiple reasons. Anyway, you can fix that by ensuring that IMDb rating has a default of, in this case, 5. You can set it to whatever you want. So when you're projecting, you do source node properties, source, IMDb rating, coalesce, source.imdb rating. That's our property that we want. And then you just specify that the default is 5. And we've done the same for start year, and we've done the same for our target node properties. And so we can create that projection. And there we go, projected without issue. And now if we move forward and we run fastrp.stream on the user movie with properties, which is not the one we just projected, it's the one with the relationship properties. And we run that, fail to invoke, non-property for start year. So here's the problem. We tried to run fastrp without specifying all the properties. And so some of our nodes don't have those properties. And this is the error message that you're going to see. That just means that you need to go back and you need to make sure that every node and every rel has the properties that you want. With the use of defaults, so if we go to our movie network defaults, which was this one, we can run that. And now it works. Ta-da! Same graph, same nodes, same everything. The only difference is that we added defaults to it to fill in those blanks. So it's super, super important to do this. So before running an algorithm, ask yourself, does this algorithm support my graph structure? So you need to check the header attributes in the GDS docs, really important. Does it need undirected relationships? Leiden does. Another question that you should be thinking about is, does it operate better with undirected relationships? Do my relationships have a deeply undirected nature to them? Excuse me. So even though it might run, is that actually the best way to run it? Who knows? It's up to you. Should I use weights? Does it matter? So on a logistics graph, for example, does it matter that it costs me more money to go from this train station to this train station than via ship around Europe somewhere else? Well, yeah, in logistics, it does matter. So now you have a cost, a weight. So you need to ask, does this actually affect the output? Do I need node properties? So again, do you need node properties? And what direction makes sense? What am I actually measuring? So this is not the same as do I need undirected versus directed? This is, let's say I do have directed. Well, which of those relationships should be directed and in what direction should they be directed? So again, going back to the customer purchases product example, maybe you don't care, maybe you're not looking to see how many products a customer purchased, but your graph is modeled in such a way that that's the information it's giving you. Well, then you need to reverse the direction. Okay. So that is just a quick reference for you. You can come back to that later. And we are going to progress. And we are now into module 2, where we're going to get hands-on with a use case. Now, I didn't actually see the poll. Did anybody answer the poll? Nobody answered the poll. Okay. So here's what I'm going to say. I'm going to answer this question in the chat. And then I'm going to say that we take another 10 minutes. In the time that it takes for me to answer, I think was it Nirav's questions? Yeah, Nirav's questions here. Either answer the poll or chuck in the chat, 10 minutes or 30 minutes. It's up to you. I'd vote 10 minutes, but you guys do whatever you need, and then we'll be democratic here. So Nirav, for context, I'm currently working in the sports betting industry. Boom. I'm exploring a transition from traditional multi-class classification to graph data science approach for a complex recommendation engine. The data is highly hierarchical. Users interact with selections, which belongs to markets, which are nested with events. A single transaction, a bet, can be either a simple path, user selection, or a complex multi involving a collection of 5 to 10 different paths across disparate events. How does Neo4j GDS handle similarity between users when their overlap is structural, e.g. they bet on the same types of markets rather than just the same selection? Also, for this hierarchical logic, is it better to use node similarity or node embeddings like FastRP? Nirav, that is such a good question. And that is another course in and of itself. But let me try and answer in as broad terms as I can. Your Neo4j GDS, let me answer them backwards as I remember them. Node similarity and FastRP are not necessarily mutually exclusive. You can use them both. They both do slightly different things. Well, they both do very different things, actually. So again, it depends on the question that you're asking. But I would say if you're working in the sports betting industry, we can probably get in touch with you afterwards and have a deeper conversation about that. Because, yeah, that's a whole other course. Node embeddings would be useful for a model that specifies categories. So you're probably used to, in using relational data, having users with attributes that's in this category. With Neo4j, you could do that. It's like our movie graph within genre. That's fine. But it's way more powerful than that. So you can model every single interaction that a user has had. And then you can categorize those interactions. Then you can project a graph model based off the relationship between the user to the category through their interactions. You can aggregate those relationships, which we haven't covered here. And then you can run node similarity. Or then you can run fast-RP. Or you can just run fast-RP on the entire graph. There's a bunch of stuff you can do. And that is off the top of my head how I would do that. But the thing to really understand with networks, and Neo4j particularly, is so I have a student that I'm working with at the moment who asked me, I'm working with Neo4j. I'm starting to import my data, and I've got 100 relationships in here. How do I know when it's too many? Don't worry about it. You can add as many relationships or as many nodes as you want within reason. I mean, I locally, in my database right now, I'm working on a patent graph for international patents, and I have 250 million nodes and 1.5 billion relationships on my, I think it takes up 300 gigs of space. Now that's problematic for projections, and I am going to shave that down, and this is all part of a bigger modeling process. But yeah, don't be worrying about that. You can have whatever model makes literal sense and answers the question that you're trying to answer. Just do that. But yeah, let's talk afterwards. And in addition to the questions earlier, with me coming from a network X background, what are the primary performance overheads I should watch out for when moving these large-scale hierarchical traversals into the Neo? Yeah, so you need to be aware of your heap. Depending on what your implementation is, you need to make sure that your heap is configured. So if you're using on-prem or you're using your local desktop version for this, not sure what you're using, then you need to make sure you have enough heap. If you're using Graph Analytics, you just need to make sure that your graph session has enough memory. And yeah, just be aware that same as Network X, Network X runs in memory as well. And like all this stuff takes computation. So certain algorithms are going to take a lot more. Like fast-RP, as it says, is fast and doesn't use actually a ton of memory for what it's doing, which is why it can be more useful than other things. So node similarity, which can sometimes be a stand-in for fast-RP or vice versa, uses a ton of memory because it's literally pairwise. It's literally going, right, for every node, what is the most similar node? Let's count up all those relationships. But still, on relatively large graphs, it has really good performance because graphs are using relationships as a first-order data type. It's not like a join in relational where you're going, oh, God, I've got to join this to join this to join this to join this. And now, well, maybe at my eulogy in a few years, somebody will be able to tell everybody what I was running. No, you can actually just run it normally. I really hope that answers your question. But if not, let's definitely talk later. I answered the poll immediately after it was posed. 10 minutes. Okay, we have an answer, 75%. Fantastic. Thank you, Jan. ROC, VPN network warning, GitHub codes using create. Yeah, so with the ROC, with the GitHub code space, it takes about 15 minutes to set up. So just don't run anything, you'll know. It'll stop moving around. It's basically, we could have gone for 10 minutes setup and then have everybody set up ENVs and do all that. I went the other direction and went one-click setup. So it takes about 15 minutes. So just leave it all there. Don't change anything. It should just run for you. Margarita Mucciarelli, I do not see any questions in the Q&A. Are they public to all of us? Oh, good question. I have no idea. Bron, maybe you could answer that. Thanks, Henry Colley. That is super useful. Awesome. Glad that helped. ROC, it is running. Look at the bottom. Yeah. So I'll tell you what, let's take our 10 minutes now and come into the community detection lesson. straight after. So we will come back here at 27 minutes. No, it's now 37 minutes past the hour. And I will see you all in 10 minutes. All right. Hello. We are back. Well, we're not. You have another 2 minutes. But I missed you all so much. I came back early. Margarita, to answer your question, I think Bron has responded to you. Yeah, no, they're not public. Okay, so I'm going to book the trend here. I'm going to say scrap the Q&A to those that can hear me and just stick them all in the chat. The reason for this is I think it's useful for everybody to see what everybody else is confused by. I didn't realize that you couldn't see the questions in the chat. I think that's good for people to see. Christian, I assume you've dropped out already, but if you can hear me, thank you for coming. And yeah, no worries. It is a monster of a session, so I do understand. If you guys could let me know if/when you are back, that would be great. And I will share. Fernando, long time no see. R, hello. R, Holger, hello. Back. Daryl, back. Hello. Back. Yes, I'm back. Okay, we're back in the game. Okay, we'll start in one more minute. Who's got a joke? See if you can type a joke in your favorite joke in 1 minute before we start. And I promise I will laugh. Back in black. Okay. Was that the joke? That's good. We are back in the black. To be fair, okay, joke time is over. It's serious time now. It's now 12:37. I also noticed that there was a severe lack of emojis. So I'm pretty sure you can send emojis now because I think I turned it on. Is that something I can do? Active emoji? Active emojis. Okay. Emojis may or may not be enabled. Please feel free to test out our emoji game. They're kind of standard emojis. I will see. Yeah, boom. We've got emoji. We're in Emoji Town. Okay, amazing. So in the future, now that I know we have this fantastic feature, I'm going to try and get, we have an internal emoji that is Keanu Reeves going, Party Keanu, he's called. I'm going to see if I can get that in this platform because I love Keanu Reeves and it's a great emoji. Anyway, on with the show. So in this module, this is all we're going to get through for today, but we will have a little, sort of a little debrief at the end before we knock off to talk about what you can do, and then maybe we can see if we can do another workshop for the rest of it at another later date. So at the moment, we're going to take everything that we've learned in Module 1, and we're going to apply it in context to a use case. So that is community detection for fraud. Okay. Now, what I want you to do is I want you to think about this not as, again, I've used the word playbook a few times. Please do not think of this as this is how you do community detection for fraud. As we've discussed and as I've harped on again and again, and I will keep harping on about, every time you run an algorithm, it is dependent on the projection model that you are running the algorithm on. So your fraud detection for spammers on social media requires a different model, no matter what algorithm you're using, to your fraud detection for financial transactions. And even within that network, financial transactions, which is what we're going to deal with now, we're going to use a peer-to-peer financial network. We're not necessarily using internal banking data. And all of that has different requirements. So again, these are playbooks. These are try and think about how they work so that you can then transfer them into a different context. So like, what is the algorithm doing on this particular projection and why? Not necessarily I run this algorithm and boom. Do not touch env pw in code spaces. Yes, ROC, that is absolutely correct. Do not touch the env because I have set it up for you. Now you can add to the env, but do not change what's already in there. Do not edit what's in there. If you want to, you can go delete that code space and then restart it. You will have time to do that. And I'm not 100% that we're going to get to the notebooks anyway today, so you will be running them in isolation. But let's mush on and see if we can get there. So, ready? Let's go. Fraud detection. We saw this graphic earlier on. This is kind of what our fraud network looks like. Users are sending money to other users who are labeled as fraud risks, who send money to fraud risks, who send money to fraud risks, who share IPs with other fraud risks, who share cards with non-fraud risks, who send money to fraud risks. Imagine trying to do this in a table. I think you would probably go mad. So, graph algorithms excel at working with and finding all of these hidden groups and relationships. Fraudsters actively try to hide, right? So with the problem that we explored earlier on with the table is that you might be a fraudster who sets up an account in one name, and then you set up an account in another name, and then you set up an account in another name, and then you've got a mate in another territory who sets up another account, or you're using VPNs, or you're doing whatever. The basic kind of fraud stuff. That is very hard to uncover or predict inside a table. But in a graph, we actually model these relationships very literally. And this is what I meant earlier when I said that at first it seems like graph is more difficult, but actually in reality, you're de-abstracting the data. For a table, you're abstracting it into a format that kind of will work for analysis. But with graph, you're de-abstracting it or just literalizing it into a format that works for both analysis and exploration and understanding. So here we've got a user chain of transactions between all these users. And even though these users down here aren't necessarily connected to the same things as these users, you can see that ultimately they are all connected to this one central user. And we might find that this user, for example, who uses the same device as this user and the same device as this user, even though they're two different devices, we can say that if not all the same person, all of these users are in a similar category. Now, it is important, and we'll talk about this in a moment, but it is important to realize that just because users are connected and one of them is fraudulent doesn't mean they're all fraudulent users. And again, this is about modeling. This is about understanding the data and exploring the data, because some of these connected users might be victims. So, someone gets, I think my dad got a spam text there a week or so ago about, hey, Dad, can you send me money because I need a new phone because I've lost my phone, blah, blah, blah. Had my dad actually done that, then he would be in this graph as a user who had sent a transaction to a fraud user. That doesn't make him fraudulent. That makes him a victim, but he'd still show up in the same graph. So let's see these principles in action with a real fraud network. This peer-to-peer financial transactions data set is actually a real data set. These are not made up. This is not synthetic data. This is real financial transactions from a real data set of peer-to-peer financial transactions. We have users, and those users have cards, devices, and IP addresses, and they have P2P transactions. They have has CC, has IP, and used relationships. Let's have a look at our schema. If you go to this slide, you just run that. Now, remember from earlier that this is a Frankenstein database. ROC, you are actually bang on the money. I was going to mention that. The Panama Papers is a really, really good example. So Neo4j was used for the Panama Papers, for the Paradise Papers, for a bunch of other stuff, and revealed a bunch of offshore accounts. It actually did affect a lot of that. So Neo4j was instrumental in the beneficiaries of those shell companies having to be named at the source, which is now European law. as far as I'm aware, and it might be US law now as well. And so when you set up a shell company now, you are legally required under international law and your home country's law to say who the ultimate beneficial owner of that shell company is. And that is directly related to running fraud detection and setting up graphs just like this. But yes, you are right in the fact that it didn't go as far as it should have or could have. That is unfortunately the world in which we live. So the fraud risk, yeah. So here I've changed user to user P2P. Just bear that in mind because we also have users in our movie graph. And I just needed to make sure that they were separate because otherwise these would be modeled as the same person. It's a really great example actually of modeling, to be honest, because you might have a graph where you have several different kinds of users and they are categorized differently. In that case, you need to make sure they're not just all users because now you have falsely modeled what users are when you're treating them in your mind as different categories of things. So let's move forward. Here you can see the scale of the data. So let me just pull this back a little. So if we match n where user P2P, blah, 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 blah. This is kind of a complex example of this query. Just because we've got the two databases, you wouldn't need to do all of this filtering in reality if you had just a single database. So yeah, you've got 800,000 nodes and 1.8 million relationships, thereabouts. If we match our user P2P, where they have a labeled fraudulent transfer of money, we can take a look at them and see what they're all about. So let's just open that up a little bit more. Let's see. Okay. So here we have this user. And we can see that this user has committed a fraudulent money transfer. So let's expand that user. And let's have a look at the other things that they have done. So here is the IP. And there we go. So the green ones are IP. The red ones are cards. And these dark green ones are marked as fraud risk. So this user, even though they have been part of a fraudulent transaction, is not marked as a fraud risk, but you can see that this fraud risk user has a ton of transactions to this user, and they share a device, they share a card, they share IP, several IP addresses. So we've got a lot of cool stuff in there that we can check out. But as cool as this is for exploration, my graph does not have the fraud risk nodes yet. Interesting. Are you... Well, there is only one graph. So what you might find is if you click on them, so the fraud risk nodes are users as well. They're actually so in Neo4j, you can do multi-label. So if you click this green one, you'll see that it's labeled fraud risk and user P2P. So that might be what you're seeing / not seeing. Yeah. Get back to me on that. Have a little explore and let me know if they are there. But for now, let's just mush on. You can explore all these. It's not a particularly efficient still movies. So in the sandbox, if you go to, let's go back. Are you running this exact query where user P2P or an IP or card or device? So you do need to run this exact query. And just to see that they are in there, if you go to call db schema.visualization, you run this. And let's just get rid of that. And you should see that you have two graphs. So you can zoom out here. And you'll see that you've got your movie graph here, and then you've got your financial graph here, which is a different graph. So let me know if that works. If you go into your overview node labels, you should see a bunch of different node labels. If not, goodness, I don't even know how that could happen. Potentially go back to your Neo4j sandbox, and you should see your sandbox in here, and then just go down to terminate, terminate that sandbox, and then refresh the page here, and that should give you back. Jan, I have the two graphs, but somehow in schema, the fraud risk is not in. Okay, so if you have the two graphs, are you saying that you can see fraud risk, or you can see user P2P, but you're not seeing fraud risk down here? In that case, given the limited time that we have, I'm going to run through this. And in the meantime, try that terminating the database thing. But I really can't see how that could have happened unless somebody deleted nodes. Not that I'm saying you have done that. I just can't think of any other way. But that would have happened unless it's connected to the wrong database. Let me get someone from tech support. Hello, this is tech support. Hello. Okay, I have sent a tech support message to the master of Graph Academy. So let's see if that works. For now, while that's getting sorted, I will push through. And then if you could just let me know after you've terminated the current database and refreshed this page, just let me know if that resets up for you, and we can take it further and see what we can do. So fraud money transfer. What you need to notice here is unflagged users connect. How many of the unflagged users connect to each flagged user? So if we run this again, you can see that they've connected. Our flagged users have connected to a bunch of different users. Some of them are flagged and some of them are not. In this case, our user P2P is pink, and if we expand here, we will find somewhere in here fraud risk users. So here we've got one here who's connected in here. You can see that there really aren't that many of them, but where they do exist, they've made a lot of transactions and they've done a lot. So Judith, you cannot isolate by graph name. The reason that we're doing it this way is because in Graph Academy, we have a sandbox instance that you're connected to. And I needed to be able to show you multiple graphs, but it's not actually something that we do because your graph is your graph. And if you had another graph, you'd have it in a different graph database. So I've kind of Frankensteined these graphs together so that I can demonstrate multiple contexts for you. But you generally would not do it this way. So what types of nodes, cards, devices appear in the neighborhood? And do you see any shared infrastructure between flagged users? So you can explore that graph if you have it. Can you guys, anybody who does have it and it is working, can you let me know? Just so I can kind of get the scope of, is this an everybody problem or is this a specific problem? That will help to uncover what the issue is. So if you do have fraud risk users and these other graphs in here, then do let me know. Harry works for me. Okay, that is good to know. So that tells me that the problem is very likely that you need to terminate the instance from here, from your sandbox. So you can find that link. Tell me this, Stuart, fraud risk users, do you, when you run the schema visualizations, specifically this, do you have them? This is the question, because what you might find is that when you are running this, there are no fraud risk users in the nodes that you are expanding. That would make sense. Ivan, yeah, it will take a little while to reload. You have user P2P nodes with fraud money transfer properties. Okay, guys, okay, I see what's happening here. I think what's happening here is you're running this query, and do correct me if I'm wrong. You're running this query, which is match n where user P2P, blah, 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 and you're running that query, right? You're getting the node count. Then you're running match user P2P, and you're getting these, which are just user P2P nodes. They're not fraud risk nodes. You need to double click these and expand, right? And even when you do that, it may be the case that these users are not connected to fraud risks. So there may still not be. You need to click around other nodes, and eventually one of these green fraud risk users will appear. To see whether they are actually in your database, you need to do call db schema.visualization. And if you have this node here in your visualization, then you do have them. If they don't appear there, then Okay, for now, let's skip it. Leave your schema as is. Don't terminate your database, because right now, it doesn't really matter. Because if there's no fraud labeled in the database, we're going to label them anyway. So let's ignore this for now and move on, because it's one of those little details. I'll sort it out afterwards. When you come back to the database later, we should have it figured out. But for now, let's go to this slide, slide 9, transfer chains. I have someone in the background working on it. And match path user P2P, P2P times 5, which gets you 5 paths, or 5 hop paths to user P2P, where user fraud money transfer equals 1 and U2 fraud money transfer equals 1. Excuse me, and they're not equal to each other, and return the path. So for now, as I said, ignore the fraud risk label and just go with user P2P. We don't need to focus too much on it for right now, because labeling fraudulent users is what we're trying to do, so we will end up labeling them anyway. So here we have this user is conducting all of these P2P transactions to this user, who's conducting all of these P2P transactions to this user, and only has one to this user. And again, we're just exploring here. We're not looking for anything specific. We just want to see kind of what this graph is telling us. Users in the middle of chains are often not flagged. So if we look at this fraud risk user here, which in your case may not be flagged, but should be here, fraud risk equals 1. And then the next user is fraud money transfer 0, and they are not labeled as a fraud risk. Yay! That's awesome, Daryl. Great stuff. They're not labeled as a fraud risk. Do you know what might have happened here, right? And I might have actually confused myself, and by extension confused you. This may be a database that I've already rehearsed on for this workshop, if you can believe that I rehearsed anything at all prior to this research, or prior to this workshop. And I may have already run all these transactions, which is why you're not seeing fraud risk, and I am. But I need to double check that. So apologies if I've confused everybody. But for now, ignore fraud risk users. Just go with user P2P. So this user P2P is not labeled as a fraud risk user in their properties. And the next one has no fraud money transfer and is not labeled as a fraud risk. But we can assume, right, some of these users are probably part of this fraud network. So money flows through these intermediaries intentionally or not. So you have been defrauded, okay? You are not a fraudster, but money is flowing through you and is connected to the fraudsters. Or you are part of the fraud network, or you are just the same fraudster using a different bank account. Tons of different ways, but this just shows you how that money is flowing, right? So let's say we've got a lot of these shared credit cards, right? So two known fraudsters sharing the same credit card. That's pretty suspicious. Okay, so we can run that. Let's have a look. Let's see if we can get this to open a little bit more. Okay, that is something we will have to sort out. But for now, let's just have a look at this. So we've got all these little sub-networks here that are Babik. Yes, got the chain. End nodes have fraud money transfer one, but boom. Okay, cool. I'm an idiot. My apologies. Moving on swiftly. Don't look at the man behind the curtain. So moving on swiftly, we can see that this particular user, these particular users are sharing these cards, right? Like look at this. Look at all these cards that all these users have that they're sharing. And then they're making transactions with these cards, right? Let's expand this user. And this user is connected to other cards. So we can pretty much assume that these people are, I mean, it screams fraud. If not, then, you know, it's an anomaly. And this is the thing we need to be aware of. There are anomalies. They do exist. So we can't just immediately go, graph says fraud, go, go, go. That's just not how it works. We need to be aware of the data model of our business domain. We don't just make decisions based on, you know, raw outputs. But anyway, it's suspicious, but it's not something we can act on right away. But finding the connections between known fraudsters, it's not remarkable because we already know they're fraudsters. So who cares? Like, we know. Yeah, cool. A table can do that. We've marked this fraudster as a fraudster, and we've marked this fraudster as a fraudster. And now we can see that they both have the same card. Cool, that's easy. But where graph comes in is we can use all these patterns to find other people behaving fraudulently in the network who have not been marked as fraudsters. And this is something that is very difficult to do in another format. And that's what we're going to do. So we're going to first explore the network, right, using Louvain, which we discussed earlier, to reduce the search space of networks. What we're going to do is we're going to say, right, community, community, community. We're going to separate them all into communities, just like we did with the actors. And then we're going to say, how many fraudsters exist in each community? And then we can say, right, well, 90% of these communities have no known fraud at all. So now we can just discard most of this. So instead of having to look at each individual account, we can really reduce that to a much smaller, more manageable number. And if we wanted to, we could just stop there. But we're not going to, are we? So we need algorithms to narrow the search space and to rank suspects, so we know who to investigate first. Before running these algorithms, we need to decide what we're going to project. This network is heterogeneous. It contains multiple overlapping node and relationship types: users, cards, devices, IPs, P2P transactions, has CC, has IP, used relationships. And it looks something like this. This is not a phenomenal model to run graph analyses on, because what is it telling us? I don't know. That is why we need to project in a particular way for a particular algorithm. So monopartite, user P2P transactions to other user P2P. It captures direct transaction networks. So who sent money to whom? And that shows us shared infrastructure. It shows us shared user communities, and we can separate them and cluster them. Bipartite, user P2P to card and device. Now we can see, like actors to movies, which users are sharing all these different cards and devices, and IPs if we want to. And we can use node similarity to see which users are really similar. And heterogeneous, everything graph. There are ways we could use that. We're not going to do it right now. But yeah, you could. So for fraud detection, shared infrastructure is critical evidence. We'll project users, their cards, and their devices together, right? So here's our main graph: card, device, user, IP, user. Okay, and instead of projecting this, we're not going to project the IP. We're just going to project the user to user and device and card stuff. Now, the reason for that is because IP addresses contain noise, which I think I hinted at earlier on in the workshop. And that is because it's not illegitimate for users to use the same IP address. Coffee shops, public libraries, what have you, office, hot desk office spaces, whatever. So it's not a great signal. And again, this is something we need to consider when we're modeling these graphs is, like, does this node that we're using is like, oh yeah, more data, cool. But is it actually providing us with legit signal? Yeah, ROC, VPNs, exactly. Is it providing us with legit signal, or is it actually providing noise? More is more with graph, yes, but more quality is more. IP multiple hops, yeah, you could do that, but now we're talking about a completely different model. And now we need to question how the new structure of that causes even different issues again. And you could intermediate that, and there's a bunch of stuff you could do. But simple is also better. So the simpler you can make it, exactly, ROC, quality over quantity, the simpler you can make your projection, the more interpretable it is to you as a human, the more explainable it is, then the more convincing it's going to be for other people. And really, the more convincing it's going to be for you, the better you can understand it. So keep it simple, add layers on top. Don't go for everything and then try to pare back layers, because in practice, that just won't work. So community detection, find groups of containing known fraudsters, and then centrality, you can rank users within that group. So let's formalize our approach. What is the question that we're asking? Who else is involved in fraud networks? What do we need to project? Users, cards, and devices with their relationships. Algorithm, we're going to use community detection and then centrality for ranking. And the config, we're going to start with defaults, and then maybe, perchance, we will refine based on the results. And I missed something there, but that's okay. Let's continue on to the next lesson. We have 20 minutes left. Let's see if we can blast through this. Okay. So Louvain is what we're going to run first. It is a community detection algorithm. It finds groups of nodes that are more densely connected to each other than the rest of the network. We've covered this in a little bit of detail. We're going to go into more detail now. Louvain optimizes modularity, which is a measure of community quality. So this example here has high modularity, and this example here has low modularity. This example also has low modularity, and this example has very low modularity. That can be quite confusing at first, which is why I've given you these 4 illustrations, right? You can see here that these little groups are clearly groups. They're just obviously groups. They're more connected to each other than they are outside the group, and Louvain clusters them and assigns them to communities in that way. Here, they have fewer community connections together than they do to other communities, and so they've got lower modularity. It's less simple to cluster them into specific groups, but you still can do it. They'll just have lower modularity. And then low modularity, even though we've got this huge density of connections, we've got way more connections between them, it's still low modularity in terms of, like, if this is your whole graph, like there's no group. They're all connected to each other. And on a complete graph, which is where every node is connected to every other node, you've got 0. And on this very low graph, well, again, it's the same. Okay, they're not all connected to each other, but they're all just connected in a kind of circular chain. So, like, how do you even split that up? Well, you can't. And so that's what we're talking about when we're talking about modularity. And it is the most important thing to remember for Louvain. High modularity, very good. Clusters of communities identified. Anything below 42, 40, Down from there, is it noise? Is it real? Who knows? And here you've got a graph, you've got a table explaining that. Increasing modularity, here's how it works. So we've got a community, a community, a community. And here's a node that we want to assign to a community. So if we attempt one, Louvain is literally going to assign it to this community and then recompute the modularity. And the modularity goes up to 0.44 because now everything is more connected. But then it's going to try it again. And it's going to put it into this community. And you can see that it goes down because now we're reducing the number of internal connections because we can see that it's only got one connection to this community. And then finally, we win when we put it into the community that increases the overall modularity, right? So now we've got a modularity of 0.46 because now this is the max number of connections internally that a community can have with the fewest, sparsest connections between itself and other communities. I won't harp too long on that because for some people that will click and for some people that won't immediately, but just really spend some time thinking on that. Like it could be now that it's clicked, it could be quite intuitive to you, or it could be weeks from now before that clicks. But I promise you, if you think about it a lot, it will click. So Louvain repeats two phases until modularity stops improving. Local optimization, which is what we just talked through, right? And then it does its aggregation step, which is basically where it takes all these communities it's identified in level 1, and it says, right, all these nodes, they're actually just one node now. We're just going to call them one node. So then it can rerun exactly the same step, but on these new nodes. So these are the same communities identified here, but they're just treated as one node. And so you can see that this community has 1, 2, 3 relationships to this one, and it's the same here, 1, 2, 3, and 1, 2, and 1, 2, and 1, and 1. And so that's what it's doing. And now it's going to recluster all of those again and again and again, hierarchically, until it just can't get any better, can't get any higher modularity. I think that was clear enough, so we won't do that one. The two-phase process creates a hierarchy. So let's say on level 0, here's our graph, and it's identified these communities. So now it goes and puts them into these communities. So it's the same structure, same modularity. They're just all condensed and collapsed into single nodes. And then it does it again, and it collapses them again until it just cannot do it anymore without messing up the modularity. So before applying this to fraud, we're going to run it on the movie graph just so we really, really get it. So we're going to project that actor-actor collaboration graph. I'm not going to go through it in any detail because we've projected it a bajillion times at this point. So you can just run that and it will project it for you. Call GDS Louvain stats. Let's run that. Cool, and here we get our stats, and we've got 0.62. That's pretty good. Louvain has some non-determinism in it. So every time you run it, it will be slightly different. That's okay. But it is also why we're not going to use it for actually saying this user is fraudulent. So if we now run louvain.stream, now that we know we've got good modularity, again, we're seeing those communities that we saw earlier. Again, we won't harp on too much about those. Now, we're going to see how actors in a community connect through shared movies. So here is a community from that. And we can see that all of these actors are shared. All of these actors, this is that first Timothy Spall network, right? Down here, Timothy Spall, Colin Meaney, and thanks, Harry. See you later. Up here, we can see how they're all connected to each other. If we move on, configuration options, you can change your max levels. So that hierarchical clustering, those are levels. So we're telling Louvain with max levels how many of those we want it to do. So with max levels 1, we discussed this earlier, we have a modularity of 0.6. And with max levels 10, we have a modularity of 0.62, right? And notice as well that our communities are different. So with max levels 10, we have 37 communities, and with max levels 1, we have 258 communities. That means that there are 258. I only got a community count of 37 from running the stats. Yeah, Bhavik, that's absolutely correct. That's fine. So you see here, I've got 37 on max levels 10. That is actually correct. So by default, by the way, Louvain will run at max levels 10 unless you set it. So when you do max levels 1, it only does that first clustering operation. So it does the first community assignments, and then it goes, cool, whatever, we're done. We're only doing one level. When you do max levels 10, it'll keep going until either it stops converging, like until modularity stops getting better, or until it reaches max levels 10. So moving on. Use fewer levels when you need granular specific groups. You're going to do detailed investigation of tight clusters. Use more levels when you want to cast a wider net. Instead of guessing max levels, you can run with, in the config, intermediate communities equals true, right? So when we do this, what we get is apparently no changes, no records. Fantastic. Okay, I need to refactor this query. Oh no, it worked. Sweet. Don't know why that happened, but fine. So what we get are intermediate communities. So you can see name, level 1, level 2, final. Those are the intermediate communities because it ran 3 levels. So 50 Cent is in community 13462, but then gets put into community 17955. And then in the third level, gets put into community 13267. So that's that actor / rapper getting put into different communities at different hierarchical levels. And you can save them and you can write them to the graph and you can look at different levels of communities separately. So we can run this to see the different increasing sizes of the communities at each level. So you can see the level, community count, average size, min size, max size. And yeah, it's kind of hard in this format to see that, but I'll let you guys run through that on your own. So it should look like this, basically, where you've got level 1, community count. Here, one has 1,578 communities. The average size of those communities is 23, minimum size is 2, and the max size is about 10,000. And then you can see again, community count reduces again, and then stops actually reducing and stays the same at level 4 because we only ran 3 levels. Cool. And unweighted, weighted. Let's see this in action by running Louvain twice, once unweighted and once weighted, because we were talking about weighted communities there earlier. This is kind of the behavior you might see, unweighted here and unweighted collapses into this, but maybe with these weights, it would collapse into a more granular structure. And you can see that happening here. So if we do GDS Louvain.write and we're doing it on community unweighted here, we get 37. And now we're going to run it with community weighted. And now we get 43. But notice this, we have more communities and they have a higher modularity. So this is just, when we run it with weights, it's just better. We have more, that means that we haven't like globbed a bunch of people together who shouldn't live together. And we can actually see this if we find actors who are together in an unweighted run, but split apart when weights were applied. So here we have Julie Graham and Georgina Hale, right? You don't need to recognize their names, that's okay. But if we expand them, right, we see that they actually only have one relationship. Thank you for a wonderful workshop. I need to drop off now. Rishikesh, thank you so much for coming. And yeah, hopefully see you on Graph Academy soon. And yeah, so we have these two who both acted in this movie, and they only have one relationship. So really, they shouldn't be together. And here they are in their wider network. We'll actually skip that query because we've basically just shown that. And then if we go and find actors who were in different communities unweighted but joined together when weights were applied, Jill Ireland and Charles Bronson, you can see how many movies they have been in together. Now, when we hadn't weighted it, they didn't get clustered together. But now that we've added their collaboration weights, how many movies they've appeared in together, they do get clustered together. So we've made a higher quality clustering in this network. And then split unweighted together and then together when weighted, you can see Charles Bronson and Jill Ireland in their wider network. And I'll let you explore that yourself, but there's your Charles Bronson, and Jill Ireland will be around there somewhere. So basically, if you have weights and they mean something for clustering, use them. Louvain stops when modularity improvements become negligible. However, the tolerance parameter tells you, it controls what negligible means. So tolerance of 0.0001, or rather 0.0001, that is basically Louvain's modularity improves by 0.00001, and it will stop. It'll say that it's converged when it stops improving more than that. And higher tolerance, obviously, is the inverse. So tolerance 1, higher tolerance, gives us a modularity of 42 and way more communities, because we've basically said, right, when you stop getting like whole integer level improvements in modularity, just stop. Don't do that, by the way. I'm just doing it for demo. And then we can do scientific notation here, but basically 9 decimal places. We run that, and it's obviously going to take a little bit longer. And then we get 39 communities with a modularity of 62. So let's drop that projection. Use Louvain on huge networks when you need quick insights, you want to understand communities, great for recommendations, that kind of thing. Because it's not entirely deterministic, it's not great when you really need interpretability and explainability, because you might know from Louvain, like, okay, cool, I've got these fraudulent users or I've got these people. But if it's something that's really important like that, not to make mistakes, then it's good for exploration. It's good for understanding the patterns so that you can then refactor and use other algorithms. Okay. Okay. So movies concept, fraud equivalent. Actor nodes would be our user nodes. Shared movies would be our shared identifiers. Finding acting ensembles is equivalent to finding fraud rings, and community equals frequent collaborators in our movies concept is community equals potentially coordinated fraudulent actors in our fraud network. And now we will progress. Now, guys, we have hit 25 minutes past 1. This webinar was supposed to continue until 1:30 only. We had a bit of technical difficulty at the start. So, look, here's what I'm going to say. I'm happy to continue. But I don't want you to feel like a captive audience that has to continue. So let's do a little poll. New poll. Continue. Okay, I have added a poll here. If you could all quickly just click the answer you want. I've basically said we can continue now and get to the end of this module, or we can reschedule for a later date, or go it alone. I will say, if you go it alone, I think there is enough here for you to get going, and for you to learn at your own pace. But I am happy for anything that you guys want to do. We will be democratic about it. Okay, we've got 5 want to continue, 3 want to reschedule, 2 want to lone wolf it, 8 want to continue. I'm going to give you 30 seconds, 30 more seconds. when we shift to 25 past 1, let's make that decision. Okay, we have hit 25 past 1 and 15 want to reschedule. Cool, that's fine by me. Bron, is that okay with you?
We can do that.
Yeah, sweet. Okay, so let's reschedule this for another time and we will pick up where we left off. Joella, that is great point. But I think we will continue with the reschedule nonetheless. It's good to have the questions and stuff. I think that's actually the most valuable part of this. Because I can just chuck a course at you and I could do a webinar or whatever. But it's nice to see where people are getting confused, to answer questions in situ. So before we jump off, does anybody have any questions about what we've covered so far today that they would like me to answer now quickly, just before you go off and try this on your own? Ivan, where will the recording be available? I presume you'll get an email, Bron?
Yes, we'll send an email around and we'll work out how we can continue this as well.
Awesome. Okay. Is that all our questions? Dennis, how did you rotate the graph? I didn't. How did I rotate the graph? I don't think I did, Dennis. Maybe that was just, okay, yeah. So when you click a node, let's just, do I have an old? No, I don't. Match in live coding. So if I expand this node here, right, because this is sort of a force-directed graph, if you just click a node, you can drag it. If I click this middle node, it drags all the other nodes with it because it's force-directed. But there's no actual rotation. So I hope that answers your question. Akhil answered it for you. There you go. Great, thanks guys. Thanks for the workshop. A lot of content covered here. Bhavik, thank you. Glad you're enjoying it. No worries, guys. Thank you, Langila. I think it was just because the graph was very small. Yeah. Akhil, thank you for answering that. Tony, you're welcome, and thank you. Thank you all for being here and being so engaged. So the notebook is the module after this notebook. You can absolutely feel free to run that in isolation. Everything here is designed for you to be able to run this in isolation. Daryl, yeah, so Daryl, you don't know how right you are. The original of this workshop, original version, was that first module, which turned out to be 8 hours on its own, which I then had to rip stuff out of. So we are trying to pack in as much GDS as possible in as short a time as possible. So getting that balance right is in the works. Yeah, so if you go to module 4, Daryl, supply chains is in there. So module 4, orograph analytics, that hits you up with orograph analytics and supply chains at the same time. It doesn't so much focus on modeling supply chains. It's more about shortest paths. But yes, it's good to know that you want that. We intend to do a supply chains course. So yeah, vote. Maybe I'll see if we can get a vote on Graph Academy GDS and people can just vote for what they want. Supply chains, that actually might be really cool. Sonia, you're very welcome. Thank you very much for coming. Kenneth, thank you. Awesome. I'm looking forward to having more of you at our sessions, seeing how you use Neo4j. I'm addicted. I hope everybody here will become addicted. Judith, thank you. Ian, thank you. Joella, thank you. Andy, thank you. Akhil, thank you. See you in the next one. Nirav, awesome. No worries, and thank you too. Yes, Jan is very intense. Thank you. See you in the next one. Many thanks, guys. Thanks, Adriano. Thank you, Kenneth, again. Okay, I think we will log off. Daryl, good. All right. Thank you so much, everyone, and see you in the next one.
Well done. Webinar is now ended.